All right. This is how math became reality, a comprehensive look at the history and history and classical experimental evidence that's put forward to support the theory of relativity theory. And you can find me on YouTube, Telegram, Discord, and all that stuff here. And this is the abstract. Abstract. Special relativity is a theory that describes the relationship between velocity and relative motion among observers. In 1905, Einstein introduced two fundamental principles of his theory of relativity, namely the principle of relativity, and it's that consists of it's the constancy of the speed of light in a vacuum. And the first principle is I read that completely backwards. The first principle asserts that all inertial reference frames are equally valid, and the second postulate of special relativity is the constant speed of light in a vacuum, and it should remain the same for all observers. Regardless of their motion relative to the light source. So these postulates have had a profound impact on the understanding of space-time, and they serve as a foundation of modern physics. By assigning time to an XYZ coordinate system and utilizing c as the speed of light as the constant, Einstein was able to describe motion through a fourth-dimensional XYZ coordinate system where the axes can vary relative to each other, and then the distance or time would be then measured by the constant of c. This uses the Lorentz transformation to enable the description of how measurements in events and distances differ from an observer or from observers in different states of motion. General relativity, which is published in 1915, provides an explanation on gravitation by describing how matter and energy cause curvature in spacetime. The presence of matter and energy cause a gravitational field that warps the geometry of spacetime and influences the path of objects traveling through it. Objects no longer move in straight lines, but instead follow the curved paths defined by the geometry of spacetime, known as geodesic motion. Einstein's new laws of gravitation were validated by various proofs, including the successful resolution of the missing 43 arc seconds, the perihelion precession of Mercury, the prediction that light would bend around a gravitational field, and gravitational redshift. And there are other various indirect confirmations of the theory, like time dilation and stuff like that, they say. So continue on. Einstein acknowledged that if any of these proofs were found to be incorrect, that his entire theory would collapse. Therefore, we will examine the experimental and observational evidence presented to validate the theory and assess if it truly supports the theory. The aim here is to provide clarity on both theories, special and general relativity, and demonstrate how they conflict with experimental and observational evidence presented as proof of the theories. If relativity theory is to replace the Newtonian framework at the cosmological scale, it must prove that the concept of space-time is a physical entity and that it has a mechanical cause and effect relationship with how it interacts with physical objects and electromagnetic energy. Here we will examine the historical narratives and experiments put forward to support the physicality of space-time. And this is a quote of a quote. This is from APS. This is the author of this article quoting Einstein, where he states that in 1915, when Einstein submitted his theory of general relativity, he made the following statement: that his entire theory would collapse if the perihelion precession, or the deflection of light rays, or the gravitational redshift were not observed or predicted or whatever, to manifest themselves into reality. His whole theory would collapse, right? So to continue on, we're going to get into some prerequisites that will be helpful to interpret the information that's put forward to support relativity. So we have arc seconds, and an arc second is a degree. It's a unit of angle measurement equal to 1/360th of a full rotation. So that's 1 degree. And if you break 1 degree into 60 seconds or 60 minutes, you'll have 60 minutes of arc. So if you break that down into
69, 69.
Yeah, right. If you break each minute into 60 seconds, you can get down to a precision of 1/3600th of a degree, allegedly. And then the system continues on from there. Just to show you how it fully works, they times that by 1,000 and they get, 3,600,000 of a degree, and then they get all the way up to 3,600 millionth of a degree, allegedly. So that's just to familiarize you with how the system of arc seconds and arc minutes works. This is an introduction into tensors, geodesics, and transformations. The geometry of space-time is described by using a mathematical construct called a metric tensor. How one might use a metric tensor and might use the metric tensor framework for practical purposes. And in the example of engineering, you can use the framework to describe a Cartesian coordinate system, XYZ axis, to define all the dimensions of an I-beam, and then you can use that information to plot out like any specific point in the I-beam, and then you can introduce stress and different factors to that specific point and see how it responds all within the I-beam. So that's how the tensor situation works. It's just a coordinate system that you can use to describe what's going on with the system that you've defined. So similarly, a space-time metric describes the geometry of space-time by adding time as the fourth axis to the XYZ coordinate system. In relativity theory, the axis in the coordinate system can be bent, warped, distorted, expanded, or contracted relative to c. Could add that in. Objects in motion in relativity theory are described as in the XYZ coordinate system as traveling on geodesic paths, i.e. straight lines. By adding a fourth dimension of time to the coordinate system, they give the appearance of being able to see outside from a fourth dimensional perspective. So while we see things going in, circular elliptical orbits, if you could be outside of the system that we see in that fourth dimensional perspective, they claim that you would see everything traveling on a straight line as it moves through bent curvature spacetime. Does that make sense?
No.
Yeah,
Yes,
I mean, yeah, right, exactly. So that's just how they say it. So if you've ever heard the description where they say, think of an ant on a basketball, the ant's traveling on a straight line, but you see that the ant's traveling along the curvature of the ball. Like that's kind of what the analogy they're putting forward. All right, so it has been experimentally shown that C has variance to it. However, to mathematically demonstrate the presupposed axioms of the invariance of C, which relativity theory is entirely built upon, equations known as the Lorentz transformation are used to express how the coordinate system is being stretched or contracted in such a way as to explain the results of optical experiments using interferometry, such as Michelson, Morley, Sagnac, and others, which we will get into later in the presentation. So this is a video on tensors and how they can be used. This is an I-beam. This is the coordinate system that a tensor could be used to describe. So this area right here in the I-beam is, you can define that with the coordinate system. I'm not going to play the video, but if you want to watch it, it's really helpful for getting a visualization on the use of the tensor and how they're applying that abstract concept to space-time. All right. Prerequisites, more prerequisites. Space-time metrics and curvature tensors. These equations or solutions are used to model the effects of mass and matter and energy on space-time or on the space-time coordinate system, which describe the distortion being experienced to explain relative celestial phenomenon. So they can use these to describe like the gravitational field warps it this much, so therefore you're going to get this orbital trajectory, that kind of stuff. That's what they're saying. Commonly used metrics that we'll go over real quick, just to give you some names and stuff to familiarize yourself with. The Schwarzschild metric, used to describe space-time outside a spherically symmetrical, non-charged, non-rotating mass, such as a black hole. And there's different types of black holes, but this describes the spherically symmetrical, non-charged one and all that. And how that affects the curvature of space-time. Then there's the Kerr metric, which is much like the Schwarzschild metric, except it accounts for charge and rotation and stuff like that, because all these factors would affect how space-time curves according to how all that works with mass and energy curving space-time. The FRW metric, this tensor is used to describe the large-scale structure of the universe and the framework of cosmology. It assumes homogeneity, isotropy of the universe, and describes an expansion of the universe as a function of time. This metric is used to calculate the evolution of the universe and the properties of celestial objects such as galaxies and galaxy clusters. And the curvature tensors that they use are equations that are used to describe the curvature of space-time, which is related to the distribution of mass and energy in the universe. The Riemann curvature tensor and the Ricci curvature tensor are the two most commonly used ones, and they are used to determine the equations of motions of objects in a gravitational field and the distribution of energy and momentum in the space-time coordinate system. So that's how that works, and we're almost done with the prereqs, guys. Prereqs: spectrographs and spectral shifts. A spectrograph is a scientific instrument used to analyze the spectral shift in light emitted by a source, such as a star, separating it into its individual colors or wavelengths. This is done by directing the light through a diffraction grating or prism, which splits the light into its component colors or refracts the light at different angles based on the wavelength. In the past, photographic plates were commonly used to record the resulting spectrum. By analyzing the spectrum shift, you can determine the frequency of the wavelength of light, which provides information about what happened to the light during its journey from, the source to meeting you, or your instrument that you're using to measure it. For light traveling through a gravitational field, it is expected to lose energy, causing a frequency shift and wavelength decrease, resulting in a spectrum shift known as gravitational redshift. This is different from velocity shift or Doppler shift, which can be determined by observing whether light is blue shifted or red shifted, depending on whether the source is moving towards or away from you. General relativity attempts to make the distinction between redshift and velocity shift, which is caused by relative motion, and redshift, which is caused by relativistic conditions, such as traveling through a gravitational field along curvature of space-time. In the case of gravitational redshift, light traveling through the gravitational field loses energy, which results in a decrease in frequency and an increase in wavelength, resulting in the frequency, the redshift, resulting in the redshift of light. The spectral shift phenomenon, after presupposed corrections are made and transformations are applied, the relativistic results can be extrapolated from experiments and then attributed to the theory. So, quick overview: light comes through the telescope, hits the prism, gets broken up, and then goes into the camera and or detector. And then back in the old days, they would manually have a colored in, can't think of the word, color spectrum, and then they would compare it that way. And there's a nice video on this if you want that from the resources. We're going to watch this quick video on relative motion and Doppler shift and how it affects waves. It'll be really useful because pretty much all of the evidence put forward is related to this.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
All right, so we got one more slide, then we'll do some questions, make sure everyone's on the same page. Observational conditions when using a telescope. Viewed at a high power from the bottom of our ocean of air, a star is a living thing. It jumps, quivers, and ripples tirelessly or swells into a ball of steady fuzz. Rare is the night at most sites when any telescope, no matter how large its aperture or perfectly its optics, can resolve details finer than 1 arc second. More typically, at ordinary locations, is the 2 or 3 arc second seeing or worse. And that's from Mac Robert Sky and Telescope magazine, 1995. So just kind of giving you some perspective on what you can expect to see when you're using a telescope and how accurate, you can get measurements just, on your own. All right. So questions, concerns, thoughts, comments so far?
This is great. That's my question.
Thanks, bro.
It's,
I have lots.
did
Go
you
ahead.
move it from like a Saturday?
What's that?
I thought it was supposed to be like on a Saturday. I don't know. It was like during the weekday at 12.
Oh no,
I almost missed it. Is what I'm saying.
Oh no, I put it on. I put it on Wednesday last week.
Oh, okay.
So Arctic, did you have anything you wanted to question, or you want to wait till the end, or?
That's Ricky.
Oh right. Okay. So we're just gonna continue then. So so now that we've got our prerequisite information, we're gonna examine the.
I have some.
What's that? Okay, yeah, we're gonna examine the experimental evidence for general relativity. The first thing put forward is the perihelion precession of Mercury. Perihelion precession of Mercury and why it's important to relativity theory. The perihelion precession of Mercury is the gradual shift of the position of Mercury's closest approach to the Sun, the perihelion, over time. In 1846, Urbain Le Verrier observed and recorded a perihelion precession of Mercury in its orbit around the Sun. He calculated that it would precess by about 5,600 arc seconds per century. Many years later, Newtonian mechanics and relativity theory faced off to account for the perihelion precession. Here are the results. The alleged actual observed 5,600 arc seconds per century. Newtonian gravity's post-prediction is 57 arc seconds per century. And relativity theory came in with a 5,600 dead even prediction, which makes up for the so-called missing 43 arc seconds. Now, Newtonian mechanics was off by 43 arc seconds per century, while relativity theory, using the modified Schwarzschild metric, was able to come up with 5,600 dead even. Getting people to accept this calculation as proof of relativity theory was crucial. It redefines gravity as space-time curvature and gives the appearance of giving physical solutions to these mathematical concepts. And then for clarification, this is not a prediction of general relativity; it's a postdiction. He observed these allegedly, way before relativity theory. So people will often say, like, relativity theory predicted this. Well, it didn't predict it. Anyway, we'll keep going. To give you like an optical representation of what they mean by what's going on. So let's say, Mercury orbits the sun every year, and this is like the equator of the sun, and it never would go over this, right? But because of its, wobble and axial tilt of the orbit or whatever they say, the precession, it would be like the equivalent of saying that it just moves up a little higher on its equatorial, orbit. So they're saying basically like they noticed a difference of like a pixel shift of 1 pixel at a distance of 93 million miles through the bottom of our ocean of atmosphere that gives less than 1 arc seconds of viewing. And then the projected out amount that Urbain guy says that he measured, 5,600 arc seconds is 1.5 degrees. So over a century, he's saying that this happens over 1.5 degrees. and that Einstein's theory, like thank God that they were able to settle that. So before Einstein solved it, though, a man named Paul Gerber also solved it using actually the same exact equation that Einstein later tries to use. So Paul Gerber was a physicist who attempted to use modified Newtonian mechanics and proposing a medium for the gravitational waves to propagate through to set them so that they would propagate at the speed of light as well. He derived his equations from classical wave theory and implemented a velocity-dependent potential correction, which explains the perihelion precession of Mercury in 1898. So just kind of keep in mind, somebody already figured this out using already established heliocentric mythology, but they, well, let's continue going over the narrative. His theory was simple and effective and correctly accounted for the perihelion precession. Mercury might have perihelion precession and even imposed a speed limit on gravitational waves by adding a medium for them to propagate through. Despite the success of his equations reaching the result matching observations, the notion of the medium and the gravitational waves could not be derived from Newton's theories, and therefore his theory was rejected. Gerber was unable to explain the physical mechanism by which gravitational waves propagated through the supposed medium that he put in the math to give the speed limit. Which further led to the rejection of it. That's what the mainstream story says. So anyway, this is a quick look at his equation here. We got your standard Greek letter psi equals 24 times pi cubed, a squared divided by tau squared times c squared minus whatever. And then the end there. Anyway, it doesn't matter. So basically, the key takeaway here is that the use of t tau in his equation he's saying that this creates the medium for which for which the gravitational waves propagates through so that it matches c. Now Einstein uses the exact same equation, and then he later got called out for plagiarism by it, but he kind of downplayed it and acted like it's not a big deal. But anyway, so in his equation, the t stands for the total time that it takes for Mercury to complete its orbit. So same equation, slightly different explanation. And Gerber's explanation, was not good enough. It didn't cut it. Einstein came in with by saying, so in Einstein's theory, the t part of the coordinate is the fabric of space. No, that's not right, actually. Gerber's variable t propagation. All right. Okay. While Gerber's equation attempted to modify Newtonian mechanics by proposing a medium, a gravitational wave, and gravitational waves to propagate through, Einstein's theory offered an alternative explanation for the observed gravitational effects. In Einstein's theory, the curvature of space-time itself is the physical mechanism that causes the gravitational effects. The curvature is caused by the presence of mass and energy, which warps the fabric of space-time and causes the geodesic paths, the path of a freely falling object along the curve. While Gerber's explanation remains mathematically valid, the story that he gave, about the propagation through the medium and how that works didn't quite cut it. So people were more, they more favored, Einstein's or whatever. So that's what they were going to end up going with. So Paul Gerber continued. It should be noted that Paul Gerber's equations were mathematically sound. His criticisms that came for him were not equally applied to relativity theory, and they just kind of were like, oh, this story is way better. We're going to go with it. So Einstein is allowed to add terms like metric, or, add different metric tensors in, add different curvature tensors. You can literally swap out, use the transformation to get into another coordinate system. You can do all these things to make reality conform to the constant speed of c to reify his theory. But when other people tried to do that, to go along with what was going on in that time, because the ether or the medium and background stuff like that was big back then. So dude was trying to incorporate the same stuff in his math, but it was rejected for the Einsteinian. Let's see these egregious violations are tailored specific math these egregious violations and tailored specific metric equations are overlooked because Einstein's theory has a story to it, space-time, a concept that can bend, warp, and contract and expand. If you want to explain a phenomenon that your theory can't explain, you just swap in a different tensor, like I was just saying, and you're pretty much good to go. The Schwarzschild solution, or the imposed ideal condition to reify space-time solution. So this is basically a fancy way of them, not addressing the three-body problem and acting like this new system, is really good. So this is the Schwarzschild metric, and we'll break it into chunks and talk about what each chunk does real quick. So when you see these equations or hear people talking about them, you can know exactly what it all means, because it all just looks like jibber jabber, right? So ds squared is the space-time interval, which describes the distance between events in space-time. It basically defines the geometry of space-time. This little section right here is the factor that describes time dilation and gravitational redshift. So like when they get the frequencies of light that they're looking for gravitational redshift conformations and stuff, this is where that comes out of this part of the calculation. This is the time coordinate, which measures the time elapsed between events in space-time, and basically all the other stuff is how they draw angles between like the center of the spheres that they're calculating. So like the center of the sphere of the Earth to the center of the sphere of the Moon, and the zenith of the Moon to the zenith of the Earth. So measuring the polar angles and all that kind of stuff. That's what the rest of that stuff is talking about there. And so what does it all mean? The Schwarzschild metric assumes the ideal conditions for calculating gravitational effects on massless objects. So the way that they calculate the perihelion precession of Mercury, for example, they calculate the sun as a stationary, non-rotating, perfectly symmetrical, non-charged object. And then Mercury is calculated as if it has the same weight as a photon and is traveling along the curvature of space-time. And the reason that they have to do it like that is because if they add the weight of Mercury into the equation, it affects the curvature of space-time, and it wouldn't give a 5600 arcsecond result out of it. That's how that works. The Mercury perihelion precession conclusion. Theories and solutions derived from principles often do not match observed reality. And the math used by Einstein has been criticized as being manipulated to produce the desired results to fit the experimental outcome. Other competing theories that exhibit the same issues are dismissed, while Einstein's solutions are not held to the same standard. Modern physics and cosmology allows for changes to be justified by simply stating that space-time behaves differently under certain conditions and expressing that assertion mathematically. So like I said earlier, changing the tensor, changing the curvature tensor, changing the space-time tensor, like literally they can just swap out anything and go, oh yeah, it works differently this way because of the math. And it doesn't even matter if the new thing would like override, previous calculations. It's they can just swap it in and then just tell their story. However, space-time is not a physical object that can be measured, so we must trust that the mathematical descriptions and the presupposed behavior under certain imposed conditions, even if the theory cannot be physically confirmed. Other possible explanations of Mercury's rotation. So the perturbations caused by other planets having like a tug of war situation.
Easy too.
Yo, your mic's going off, Blue.
Oh, sorry.
You're good, bro.
Talking to myself.
Yep.
I'll mute it.
Thank you. Perturbations caused by other planets, so a gravitational tug of war, so to speak, with the planets in our solar system. Gravitational effects of the sun's oblateness. The sun isn't, despite being calculated as being perfectly symmetrical, non-rotating. They say that it has oblateness to it, wider at the center, wider at the equator, and flattened at the poles, similarly to how they say the Earth is. That could explain it, because you got to remember too, they're talking 93 million miles, ocean of atmosphere, and this dude's measurements, would have been way less than 1 arcsecond, to mathematically extrapolate out to 1 degree over a century. So, who knows if they even really measured that, or if this is even a real problem. Undetected. So they used to say undetected planets would cause the perihelion precession. So there was a planet Vulcan, they used to say, and that's a really funny story. If you want to watch a video on that, you can check this link here. And then there was an ether drag explanation. So there's multiple different explanations to how this perihelion precession could go. But the way that it's presented in the mainstream narrative is that there's only one solution, and that's space-time curvature, bendy space-time. Okay, so that was the last slide on that. So are there any questions so far for the perihelion precession in Mercury?
No, I mean, it's a incredible presentation so far.
When you say Einstein got called out for plagiarism, what's the story behind that, and how did he down talk it?
So you can actually look it up on Wikipedia real quick. I'll pull it up. But basically, what happened was some other physicists were like, "Yeah, Paul Gerber, solved this a while ago, and you just plagiarized it." And Einstein's response was basically, "Well, I've never seen his work, and because his work describes a medium, it's verbosely superfluous to my work." He didn't say verbosely superfluous, but I do enjoy saying that. So he just kind of hand waved dismissed it. Like, I don't know what you're talking about, bro, and your equation's dog shit. And the way that I use T in the
Sounds
equations
like him, dude.
is way better than yours. And so he just kind of punked him out on that, and nobody really questioned it or kept pressing it, even though the equations are identical. So I don't know if he plagiarized it or not, but they're identical, and there's also other accusations. I'm sure, I don't know if you're familiar with people talking about how he took the Rince's equations and the stuff from Poincare and some other guy I can't remember. I want to say Hilbert, but I don't think that's it. But yeah, so like he's been he's had these accusations come across before, so I don't know. You just kind of gotta have to decide on your own. So if there's no further questions on that stuff, we can move on to the deflection of light rays. All right, deflection of light rays, gravitational lensing. Newtonian physics and Einstein's relativity theory make different predictions for the deflection of light rays. Einstein's theory of general relativity predicted that light would deflect or would be deflected by a gravitational field due to the curvature of space-time, which is caused by matter and energy. I keep saying mass. Matter and energy, curving space-time. Newtonian physics predicted that light would bend by half as much as predicted by relativity theory and due to a different mechanism. In Newtonian physics, gravity is considered a force, and in the traditional sense, it's described as a mechanical attraction between two masses. So Newton was saying basically that light would act like a particle and it would be attracted towards a gravitational mass. And whereas Einstein's theory is saying the particle's just traveling freely through the curvature of space-time due to the mass,
Is it gone?
and that will produce the curve. Who?
NASA took him.
Oh, you cut out for like 20 seconds there. I was gonna
Oh,
say you cut out for 20 seconds there. If you just wanna go back a paragraph.
yeah. Okay, so is this where I left off in Newtonian physics?
Yeah, you're still roboting on us.
Yeah, we can't tell what to say.
Oh,
It must be the Satelloons today. Let's give it a minute.
testing.
That seems good.
Seems good. Okay, so did I leave off at Newtonian physics?
Yeah, that's about where it started getting garbage.
Okay. So in Newtonian physics, gravity is considered a force in the traditional sense, which is described by the attraction between two or more masses. Newton's gravity. Newton thought that light would be like a particle, and the gravity would act on it, like attracting it towards it a little bit. And Einstein basically said that light would just be traveling along, a geodesic path freely in space-time, but following along the curvature of space-time imposed by the gravitational field. So different mechanisms and different amounts of deflection from the predictions, right? Is what we're getting at here. So in Einstein's theory of relativity, gravity is not considered a force in the traditional sense, but rather the curvature of space-time caused by matter and energy. Differential equations in metric tensors, and that's not worded right. Differential equations and metric tensors are used in general relativity to provide the geometric interpretation of gravity, which in the presence of matter curves and all everything moving through that curvature, that's how we get the deflections. So Einstein's concept of space-time curvature usurped Newtonian mechanical attraction force at the cosmological scale to be the dominant explanation of gravity. And it should be noted that no one has ever seen gravitational lensing or an Einstein ring with their own eyes. The only evidence for gravitational lensing in imagery comes from computer-processed imageries from James Webb Telescope and the Hubble Telescope and that sort of stuff. And we'll get further into the Arthur Eddington stuff as we go. So Arthur Eddington's expedition to prove relativity theory by way of gravitational lensing. May 29, 1919, British astronomer Eddington led an expedition to the island of Principe off the west coast of Africa during the total solar eclipse. The purpose of the expedition was to determine the accuracy of 3 theories regarding gravitational influence on starlight. Sorry, I have to burp, but I'm trying to get it out without... And give me 1 second. Okay, sorry about that. The theories were no influence on gravity, or from gravity, the effect in accordance with Newtonian law of 87 or 0.87 seconds of arc, or one determined by Einstein's theory of relativity, which predicted an effect of 1.75 seconds of arc. These expeditions aimed to distinguish between these possibilities. The data he collected on that day would be used just 7 months later to solidify the direction of physics and cosmology for the next 100 years. Arthur Eddington's data: unfavorable weather conditions rendered almost all of his photographs worthless. As time went on from his initial discovery, Eddington changed his story to bolster his conviction in the evidence or lack thereof. Eddington wrote Fowler in 1919 before returning to his expedition. June 3, 1919, the cloudy weather upset my plans I had to treat the measurements in a different way from how I had intended. Consequently, I have not been able to make any preliminary announcements of the results, but the one plate I measured gave a result agreeing with Einstein. I forget the date on this one, but shortly after, June 1919, I secured 16 photographs, but only the last 6 was the sky clear enough to show any stars on them. I got between 3 and 5 images, and as the sky was generally only clear on one part of the plate at a time, the stars secured on the plate are badly distributed. However, one plate has some evidence of deflection in the Einstein sense, but plate errors have yet to be fully determined. And then, way after these events, 1920, Eddington says, the results from this plate gave a definite displacement in good accordance with Einstein's theory and disagreeing with the Newtonian prediction. Although the material was very meager compared to what had been hoped for, the writer, who must be admitted was not altogether unbiased, believing it convincing. And then later, in his biography written by Vibert Douglas, 1957, Eddington stated at some point in his life, in later years, Eddington referred to his findings on May 1919, as the greatest moment of his life. So, bit of a flip-flop there. There was originally 32 photographic plates. The expedition was split between him and his boy Cromlin. Cromlin went to somewhere in Brazil, I forget where, but he went to Brazil. All of his measurements were dismissed on the grounds that because of the temperature change caused by the eclipse, that it threw the measurements off in the telescope, like the contraction of the lens or whatever, because the temperature change and all that kind of shit. So he was completely, none of his pictures, survived or made it or were deemed worthy. And then only 2 of Eddington's pictures come through. And then it's really only just the one that he says gives good accordance with the Einsteinian stuff. But we'll get further into that as we move on. Just kind of keep this in the back of your mind as we move forward. Eddington's data continued throughout different stages of his life. I just went over all that. He went as far as to backtrack his story about the poor star distribution, later claiming in a published paper with Dyson and others in 1920, saying that Dyson and others, going back to 1920, that the 5 stars shown on the 2 plates from Principe included all the most essential stars, and even further suggested that the clouds may have been beneficial in preventing overexposure of the brightest stars. So, he's kind of flip-flopped the story into this amazing, it just happened to work out. cool story. So this is from here out on this part, we're going to be reading the transcripts of the Royal Astronomical Society, or the Royal Society and the Royal Astronomical Society meeting on November 6th, where they got together and reviewed Eddington's data and basically presented it as a solid confirmation of Einstein's theory. And this is where they go ahead and roll out confirmation of the theory and everything from there. So the controversy of the accuracy and the merit of the data collected is the mainstream point of contention in the story. However, there is a more subtle conversation being had over an entirely different aspect of the eclipse data that proves to be devastating to the narrative that the eclipse 1919 or that the 1919 eclipse supports relativity theory. Using the observatory volume 42 as our guide, we'll go through the transcripts of the meeting where these guys all got together and decided to turn math into reality. Quotes from the Joint Eclipse meeting. Sir Joseph Thomson, President of the Royal Society. It is difficult for the audience to fully weigh the meaning of the figures that have been put before us, but the Astronomer Royal and Professor Eddington have studied the material carefully and regarded the evidence as decisively in favor for the larger displacement. So, if you remember, Newton predicted 0.87 seconds, Einstein 1.75. So he just opens up with just hands down, confirming it. If his theory is right, it makes us take an entirely new view of gravitation. If it is sustained that Einstein's reasoning holds good and it has survived 2 severe tests, then it is the result of the highest achievement of human thought, and the weak point in the theory is the difficulty in expressing it. It would seem to me that no one can understand the new law of gravitation without a thorough knowledge of the theory of invariance and the calculus of variations. One other point of physical interest arises from this discussion. The light is deflected in passing near large bodies of matter. This involves alterations in the electric and magnetic field. This again implies the existence of an electric and magnetic force outside of matter, forces at present unknown, though some idea of their nature may be got from the results of this expedition. So he's, insinuating that space-time curvature is a real possibility here, and they got solid data to back it up, blah, blah, blah. So Arthur Eddington chimes in. We know that momentum is carried along with the path of a beam of light. Gravity in acting creates momentum in the direction different from that of the path of the ray, so it causes it to bend. For the half effect, we assume that gravity obeys Newton's laws. For the full effect, which has been obtained, we must assume that gravity obeys the new laws proposed by Einstein. This is one of the most crucial tests between Newton's laws and the proposed new laws. Einstein's law had already indicated the perturbation causing the orbit of Mercury to resolve. That confirms it for the relatively small velocities. Going to the limit where the speed is that of light, the perturbation is increased in such a way as to double the curvature of its path, and that is now confirmed. This effect may be taken as proving Einstein's law rather than his theory. It is not affected by the failure to detect the displacement of the Fraunhofer lines of the sun. If the latter failure is confirmed, it will not affect Einstein's law of gravitation, but it will affect the views on which the laws were arrived at. The law is right, though the fundamental ideas underlying it may yet be questioned. One further point may be touched upon. Are we to attribute the displacement to the gravitational field and not the refracting matter around the sun, the refractive index around the sun, to produce the results at a distance of 15 arc seconds from the sun? Would be that given by gas at a pressure of 1/60 to 1/200 of an atmosphere? This is too great of a density considering the depth through which the light would have to pass. So the last remark that this guy kind of made here, he's kind of hinting that the deflections only happen near the solar limb, which we're going to get to. But in Eddington, he's like, saying like, no, that's definitely not a possibility. It can't happen. It has to be gravitational, the gravitational field in space-time curvature. So he's quick to get that out from his one photographic plate and poor star distribution and all that. Frank Watson Dyson, Astronomer Royal. The day the eclipse The day the eclipse opened cloudy, but later cleared, and the observations were carried out with almost complete success. Quote from guy who wasn't even there and got, a letter in advance explicitly stating that it was shitty and he didn't get good observations. The plates were measured at Greenwich immediately after the observers' return. Each plate was measured twice by Messrs. Davidson and Ferner, and I am satisfied that if such faults lie in the results, that they are within the plates themselves and not the measurements. After a careful study of the plates, I am prepared to say that there can be no doubt that they confirm Einstein's prediction. A very definite result has been obtained for the deflection of light in accordance with Einstein's law of gravitation. So we got some support from someone who reviewed the plates as well. Professor Alfred Fuller, president of the Royal Astronomical Society. The quantity looked for, I may say, is 100 times the probable error of the measurement which can be made with the large spectrographs now employed in such inquiries. Evershade has examined the light from the side of the sun away from the Earth, photographing the spectrum of Venus when on the further side of the sun. Gravitational displacements, if they exist, should appear in all parts alike, but he finds no such displacement on the other side of the sun, though he does see a slight displacement on the near side. It is very desirable that the spectroscopic test should be repeated carefully. Professor Frederick Lindman. As to the theory itself, I must confess the fact that it is always presented in the form of a purely mathematical point of view seems regrettable to a mere physicist. No doubt that the present form is correct and even elegant once one becomes familiar with the notion. I cannot believe, however, that a profound physical truth cannot be clothed in simpler language. To put the theory in the form of curvature in a space-time manifold seems to me much simpler than the tensor presentation. Cannot Professor Eddington translate his admirable treatise to the tensor notion into some such form? So he's basically, just talking about how it's hard to convey these mathematical concepts to people, but having the space-time curvature manifold story is a really nice touch to it, and we should talk about it like that instead of mathematically, because nobody understands this shit. Professor Hugh Frank Newell. May I add congratulations on the extraordinary success of the observations. I feel that the Einstein effect holds the day, but I do not yet feel I can give up my freedom of mind in favor of another interpretation of the effects obtained. If Einstein had not existed, or had not predicted the deflection, we might have had a similar experiment to test the presence of an extended atmosphere around the sun, and we could have argued from the results back to the hypothesis. Think for the moment of the fine prominence that was seen on the day of the eclipse. It was followed by Evershade for a rotation and a half. Matter was expelled outwards in the course of the movement, as we know from the sequence of the photographs secured with the spectroheliograph at Cambridge on the day of the eclipse. And yet this matter at different high levels goes around the sun, not with gravitational velocities, but with the same velocities that hold at the lower levels of the spots. It is, I know, a cheap criticism to make a qualitative suggestion in opposition to a quantitative result, but I feel that I want to keep an open mind for the existence of matter in a gravitational field and electric forces are acting simultaneously in an unknown relation under conditions which admit the existence of an extended corona. It does not carry much weight with me that when it is urged that to explain the deflection in terms of refraction, the medium must have a density of 1/200 or 1/40 of that of the terrestrial atmosphere would be needed to produce the effect. For we have to do with the possible extended solar atmosphere at a high effective temperature, almost certainly in part controlled by electric as well as gravitational conditions existing in it. And who's to say what its refractive properties may be? I prefer to keep an open mind on this interpretation, but I wish in conclusion to add my heartiest congratulations to the astronomer and the observers on the observational results obtained. So this guy, Frederick Lindman, comes in again. Might I say one more word? Have we not evidence of motions of comets passing near the sun? That the matter outside the sun is distinctly diffuse. Comets suffer no noticeable breaks in their path. So he's saying that well, when comets go by the sun, there's no, like, their tails don't get fucked up, so there's probably not an extended atmosphere. So he kind of throws that in there. So this is Dr. Silverstein. But in spite of what the president said, I believe the results to be essentially an isolated fact. There is a deflection of light rays, but it does not prove Einstein's theory. It cannot logically be deduced from his theory that gravitational effects in absence of the spectroscopic results. I read there his theory of gravitation as the gravitational effect in the absence of the spectroscopic results. Yeah, okay. And as far as we know from St. John's and Evershade's observations, the predicted redshift of the spectrum lines of an amount exceeding almost 100 times the probable error of modern spectroscopes, as Professor Fowler has just told us, is not obtained. When Professor Lindman attempted to explain the obstinate nullity of this effect by the motion of luminous gases in the line of vision of the sun is not satisfactory, for St. John was well aware of this complicating circumstance, and therefore purposely observed as many as 43 lines at the sun's center and almost as many as 35 at the limb. Now we cannot well assume that gases move everywhere towards or away from us only to suit Einstein's theory, i.e. just to compensate for his theoretical shift effect. As I have recently pointed out on another occasion, if there is no spectral shift, Einstein's coefficient, how he describes space-time curvature, which is entirely responsible for it, must be unity. And if we go back to the differential equations, his field equations, we must see at once that the coefficient and his well-known approximate solution become unity at the same time, one being, and then he rattles off some of the equation there of how all that was derived, so that the world element reduces to, and then part of the metric used to describe the curvature of space-time. And simply, the equations of motion are given by whatever that is. We ultimately see that the spectral shift we ultimately see that the spectral shift is absent. Einstein's theory not only does not give such refinements to the planetary motions of the secular motion of the perihelion, but it does not even give ordinary or Keplerian motion. In short, the orbits of the planets would be straight lines, and the planets would move along them uniformly in spite of the sun's presence. In theory, the theory stands or falls on the correctness of the results of Evershade's and St. John's. It is unscientific to assert for the moment that the deflection, the reality for which I admit, is due to gravitation. It is, in this sense, I declare it a moment ago to be an isolated fact. The discovery made at the expedition, beautiful as it is, does not, in this circumstance, prove Einstein's theory. We owe it to that great man over there, pointing to Newton's portrait, to proceed very carefully in modifying or retouching his laws of gravitation. This is by no means defending blind conservatism. The spectral shift required is perhaps 100 times, but certainly not less than 40 or 50 times the error of modern measurement. The solar spectrum can, even in this country, be observed many times a year, and the matter can thus be decided without having to wait centuries for another equally advantageous eclipse. If the shift remains unproven at this point, the whole theory collapses, and the phenomenon observed by the astronomers remains a fact awaiting to be accounted for in a different way. So, to give a quick recap here, all that was pretty good. So we'll continue to the next one. So to kind of explain the relevance of what just transpired and who the St. John's and Evershade guys are. So we've never heard of these guys. We've only heard of Eddington and Cromlin, right? So the St. John's and Evershade guy were doing observations in tandem with Eddington's observations, and they were looking for redshift, gravitational redshift specifically, predicted by Einstein's theory as well, to match up with the star displacement, so that they could establish a cause and effect relationship with the displacement and the redshift prediction of redshift due to space-time curvature due to the gravitational field. So this was all supposed to go in tandem, which would give physicality to the equations. It would like really explain everything coherently, and it would like further support it, right? So this dude totally pointed that out, that without those redshift readings, that you can't attribute this to the space-time curvature. So to kind of go over that concept again, regarding Doppler shift, the medium of air, i.e. oxygen and water molecules vibrating to facilitate the energy transfer necessary to produce the high pitch to low pitch for relative Doppler shift in sound waves. Sound waves are produced by a disturbance in a background medium, which causes the particles within the medium to vibrate and transfer energy to one another. In essence, all waves are varying frequencies of vibration through their respective mediums. Relativity theory asserts that no energy transfer is necessary to cause redshift. Instead, it proposes that the observed redshift is due to the stretching of the photon's frequency due to gravitational effects as it travels along the curvature of spacetime. To establish a cause and effect relationship between any perceived star displacement during the May 1919 eclipse, St. John's and Evershades were tasked with taking spectrum shift observations during the eclipse with equipment within 100 times the amount of probable error required to analyze such shifts. In fact, their equipment was so good that they could take multiple observations throughout the year using the Sun and Venus, and they never found any redshift which directly contradicts general relativity's prediction and nullifies the fantastical metaphors about space-time manifolds and curvature and the distortion of time. Later, we will cover supplemental experiments that are put forward to reify relativity theory. The Pound-Repka, Pound-Snyder, Heffel and Keating, and some other ones are cited as proof of gravitational redshift, thus establishing that gravitational redshift or space-time curvature can affect electromagnetic energy. As Silverstein pointed out, without a physical mechanism for redshift to occur, the equations just reduce to stories. The lack of observed redshift in tandem with the displacement is a violation of causality and destroys relativity theory. Eddington replies to Silverstein, one word to Dr. Silverstein. When a result that has been forecasted is obtained, we naturally ask, what part of the theory exactly does it confirm? In this case, it is Einstein's law of gravitation. It is not necessarily that his theory is confirmed with the underlying assumption that ds is the quantity measurable by clock and scale, but still remains the question of what the intermediary quantity of ds is, which must be tested by the Fraunhofer lines. And the Fraunhofer lines is referring to the spectral shift lines. That's another way to say it. And ds is, of course, referring to the geometry of space-time. So talking about how alleged space-time curvature happens, what exactly is curving to cause, something to have its course altered, so he's just kind of deflecting from that. And so note ds is the space-time interval for general relativity. The subtext of their conversation is about replacing the mechanical mechanism for gravitational attraction with space-time curvature. And the fact that, that space, which would establish that space-time is in fact a physical entity, which is what it would have to be for it to produce redshift. And so, that's the end of their meeting. The following day, November 7th, 1919, even though the evidence presented on the previous day at the joint eclipse meeting held by the Royal Society and the Royal Astronomical Society was of poor accuracy and presented no accompanying spectrum shifts observations to confirm the curvature as the mechanism to cause the alleged star displacement, it was announced by Sir Joseph Thomson, president of the Royal Astronomical Society, stating that the expedition was a success and Arthur Eddington had proved Einstein's theory of general relativity. By the time Einstein woke up November 7th, 1919, he was catapulted into stardom, an overnight celebrity. British and U.S. media spreading the word of how his theory had been confirmed and that the laws of gravitation now obey Einstein's space-time curvature. H. von Kubler, 1960, Vistas in Astronomy. It should be noted that the deflection predicted by Einstein in 1915 was very small, being about 1.7 seconds of arc for a ray of light on the edge of the sun, and inversely proportional to the radial distance from the center of the sun. Since no star for which the measurements made during the 1919 eclipse were within 2 solar radii of the center, the largest deflection that would have occurred during largest deflection that would have occurred according to the theory would have been less than 0.87 seconds of arc, which for the 343 centimeter focal length of the telescope used by Eddington would have corresponded to about 0.01 millimeters or 0.00039370008 inches on the photographic plate. So even without the spectrum data, like the stars themselves, the displacement doesn't even back up these people's claims. So this is Dennis Sima, 1967, in Einstein the Man, and his achievement. The first attempt to test Einstein's prediction was made by a British expedition led by Arthur Eddington just at the end of the Great War. At a time, it was considered very striking that a group of British astronomers should attempt to test the theory proposed by a German. The results of the test were claimed as a triumph for Einstein, and his worldwide fame dates from this event. Ironically enough, attempts made at later eclipses suggest that Eddington underestimated the uncertainties inherent in such a difficult observation, and even today, Einstein's prediction has not been tested with the precision one would wish. So this is many, many years later, 1967. Subsequent observations have been done. They still can't quite get the displacement that would be like, okay, this one, guys, this is the one we should tell everyone proves Einstein's theory. So they just stick with the Eddington one, right? This is John Maddox, who was the head editor of Nature magazine in 1995. Historically, the most dramatic proof that Einstein was on the right track was his general theory of relativity. In 1919, when Eddington and his associate Crommelin took themselves to the Western Pacific to track the total eclipse of the sun of that year, they were bent on measuring the predicted deflection of light from distant stars lying near the limb of the sun. As the world knows, the prediction was confirmed within the limits of the accuracy of the observation. To general applause, Einstein became a celebrity overnight. What is not so well remembered is that the measurements in 1919 were not particularly accurate. The standard error for the measurement was roughly 30%, while the displacement of the images of the different stars in the field near the eclipse of the sun ranged from half to twice the deflection that had been predicted by Einstein. The later eclipse measurements have not been much better, largely because of the difficulties in making accurate measurements from the ad hoc observatories that have to be established. So half of Einstein's prediction of 1.75 arc seconds would be closer to the Newtonian prediction of 0.87 seconds of arc. So, and this is just some added conjecture here because I don't have the paper, but I read somewhere in one paper that I was going over that this Silberstein guy actually went through the Crommelin's data and found that all of Crommelin's data gave Newtonian agreements, and that's why we don't have any data from Crommelin, because all of that like literally agreed with Newton. So even this guy reviewing the two plates that Eddington says proved Einstein's agreement don't even do that. So they actually give an agreement closer to the Newtonian prediction. Oops, accidentally hit the wrong button. 1 second. All right, so continuing on from John Maddox, we have Edward Dowdy. And this guy, he went over the Eddington observations. He went over a bunch of other observations with the solar limb of the sun and all that, and the gravitational deflection, and found that light, or the starlight displacements, if any, only occur when they're at the limb of the sun. So in this area where there's like a supposed plasma medium, supposed extended corona, that kind of stuff, where there's an actual medium to bend light, is the only actual place where light bends. So we'll just kind of give a quick overview of this guy. Died a couple years ago, so shout out to him. Gravitational deflection, or no, these are the names of his papers that he wrote, if anyone's interested, but we're going to be focusing on these two here. And from his analysis, he has a replacement theory for why it only goes through the solar limb. So imagine, in relativity theory, right, the gravitational field doesn't stop here at the solar limb, right? It actually extends into infinity, but obviously its strength, it depreciates over distance, right? But the fact that the starlight only happens within this area, right, and it doesn't happen anywhere else, there's no gravitational field, right? Because if there was, there would have to be displacement from all the stars around it, not just near the solar limb. So when they make these solar limb observations that get a displacement, well, there's, it's actually, it's actually heliocentric canon mythology that there's a medium there. So does that prove, a gravitational deflection? Like, I don't think so. And neither did this guy. So he ended up coming up with a replacement theory for that, and he basically used using an energy or least time, or using the least time calculation that's based on the conservation of energy and momentum. He theorizes that the light's moving through the plasma that's held, and that the plasma is held, due to gravitation or whatever. But the light's moving through the plasma, and that's the plasma that's causing the deflection, and not a quote unquote gravitational field or space-time curvature. And just to give a quick visualization of that concept, so starlight further from the sun should still bend, but it doesn't, and it only bends when it's super close to the sun. So in closing on this, we have Ian McCausland, 1999, Anomalies in the History of Relativity Theory. If the findings of the eclipse expedition had been announced as inconclusive instead of decisive in 1919, general relativity would have had to compete with other possible theories, such as Gerber's, to explain certain astronomical observations, and a better theory might eventually have been found. In this author's opinion, the confident announcement of the decisive confirmation of Einstein's general relativity theory on November 7, 1919, was not a triumph in science as it is often portrayed, but one of the most unfortunate events in the history of the 21st century. So what would cause someone to say something like that? Well, a lot of the information I found was from his paper. So he went through all that and came to the same kind of conclusion. So to give a quick recap, lack of actual evidence to establish a cause and effect relationship. The real big one here is that there's no spectral lines that were predicted by the theory. And the only deflection seen happens near the limb of the sun, where there's a supposed medium. In the quote unquote vacuum of space, there's no displacement. So, all right. So in conclusion, we often hear that math is reality, despite being able to produce numerous instances that falsify that claim. It is the cornerstone of the relativistic belief system. The mathematical concepts that make up general relativity, Einstein's tensors, spacetime curvature, etc., were falsely claimed to have physicality to them, although there is no physical spacetime fabric and any bending thereof is conceptual. The evidence that's put forward requires it to be, in fact, physical. While there are other possible explanations to explain the phenomenon, only one explanation was given the stamp of approval and was seemingly rolled out overnight. We are told fantastical stories about bending and warping of the fabric of space-time, and how it can become distorted and collapse in on itself, and creating an infinite curvature loop, which nothing can escape, not even light. And yet it produces no spectrum shift in the starlight or from the light of Venus when it's near the sun. The lack of spectrograph data is the real smoking gun here. Later space-time will be proven to be a physical entity used from the Pound, Repke, Snyder experiments, LIGO, etc., and placement of the missing data, but we will go into that as we go through the presentation. And the issues in proving space-time curvature as a physical entity will become more obvious. All right, so that was a long one. If there's any questions, concerns, feel free to ask now.
I bet Biodu has one.
Yep, of course. I wanted to go back to the gravitational lensing claim. I posted in the chat microlensing events of someone that we do know, an astrophysicist, who took these, who essentially participated in this paper, microlensing of a planet in front of a star. And what he's asserted is that he's used only GR and SR to make these predictions over time, because this event is cyclical, and there's lots of data on it. Using adaptive optics from the ground, you're able to see these microlensing events. And I'm just wondering, within that realm with microlensing, what, if not for SR and GR, can we use to one it?
I'm sorry, to one what now? What was the last part? You're cutting out at the
Nope.
end.
Nope.
Shit. Maybe just a question. What if not for SR and GR would replace what we see happening as well as a prediction tool
Oh,
for these
in
events?
terms of explaining like what that guy saw if there's no space time curvature.
Well, using SR and GR, it worked and it's consistent. So I'm asking, what's a
Yeah.
replacement for it? Because the assertion would be that it doesn't exist.
Well, the calculations and stuff that are derived from that, which quote unquote match the observation, are physically meaningless, which we'll get into later in the presentation. And in terms of a replacement for it, like I'm not familiar with that. I'll have to look at it. So we'll have to go from there. But a replacement for what it would be. So when light is slowed down or changes speed, you would get these kind of effects. So if there's a background medium, I think that a changing in the speed would cause that. But again, I don't even believe in like the distances and stuff that are extrapolated from the space-time coordinate system or anything like that. So it's it for me, when you guys are like, oh, it would definitely have to be this size and this distance and blah blah blah. Like I don't even see it that way. So like it's not, it doesn't mean anything that the equations from general relativity come out to predict it, and you'll kind of understand where I'm coming from that as we get later on in the presentation when we go over the mathematical analysis of it, and you'll see how what I'm talking about, how they can perfectly work out like that just fine, and but not actually mean anything. Does that kind of cover your question?
No, but I'm excited for what you say next.
Okay,
I
cool.
thought that was an excellent answer.
All right, cool. Yeah, we'll see how it goes from there. Okay, so gravitational redshift of light. Gravitational redshift of light. The gravitational redshift is a phenomenon in which electromagnetic waves, such as light, lose energy as they escape a gravitational field or the gravitational field of a massive object. This causes the wavelength of the light to shift towards the red end of the spectrum. In this case, gravitational redshift, the energy of the light is decreasing, but the speed of light which travels must remain constant. To decrease The decrease in energy is compensated by an increase in wavelength of light, leading to redshift in the spectrum. The decrease in energy that causes light to redshift is compensated by an increase in wavelength so that the speed of light remains constant. Mathematically, this can be stated as E equals h times f, energy equals Planck's constant times frequency. As the energy decreases, the frequency of light also decreases, which leads to an increase in the wavelength. Since the speed of light is directly proportional to the wavelength and inversely proportional to the frequency, the increase in wavelength compensates for the decrease in energy, keeping the speed of light constant. In other words, the speed of light doesn't change, it only changes wavelength and frequency. The wavelength gets shorter and the frequency gets lower, but the product of the two remains that the speed is the same. How general relativity explains gravitational and cosmological redshift. In general relativity, there are two types of redshift that can occur: gravitational redshift and cosmological redshift. There's actually transverse Doppler effect too, they try to say. Gravitational redshift, the wavelength of light of an object is shifted towards the red end of the spectrum as it travels through a gravitational field. This effect is caused by the fact that photons of light lose energy as they move through or move out of a gravity well. The loss of energy causes the wavelength to stretch. Cosmological redshift, the wavelength of light. Basically, in this one, they're just saying that the expansion of the universe itself is what's causing the redshift. The transverse Doppler effect, the phenomenon in which the frequency of wave appears to be shifted when the source and the observer are in motion relative to each other in the direction perpendicular to the propagation of the light source, supposed to showcase that two observers traveling at relativistic speeds would see the same spectral shift as if they were at rest. In summary, general relativity predicts that redshift can occur due to the curvature of spacetime caused by the presence of massive objects. It explains redshift due to an energy change of a photon as it moves in and out of a gravitational well and along the curvature of spacetime. In the case of cosmological redshift, the shift is due to the expansion itself, expansion of the universe itself. we go on, we'll cover more types of redshift. Although, I did other types of redshift. Doppler redshift, relative motion to the source and observer. Time dilation redshift. This is caused by a difference in rate of time between two positions in space. And gravitational lensing redshift, which is caused by the light passing through a gravitational field, which bends the light and causes the shift in wavelength. Hubble shift. The light of distant galaxies is shifted towards the red end of the spectrum. This was observed by Edwin Hubble in the early 20th century, who found that the light from distant galaxies was redshifted, which indicated that they are moving away from us. Note, Hubble even up until his final lecture before the Royal Society always held the possibility that the redshift did not necessarily mean velocity of recession, and it might be caused by something else. Moving forward in the presentation, we'll look at two experiments that are put forward as proof of general relativity: the Pound-Repka and Pound-Snyder, which is related to gravitational redshift detection. So, Pound-Repka experiment. Pound-Repka experiment conducted at Harvard's Jefferson Tower involved emitting photons from a precise wavelength at the top and bottom of a 22.5 meter tall structure. Upon measurement, the photons emitted at the top of the tower were found to have a slightly decreased wavelength than at the bottom of the tower, while those emitted from the bottom had an increased wavelength while going to the top, and those were redshifted. There are three common interpretations of the Repka and Pound-Snyder experiments results that are used to support relativity theory, which includes invoking the equivalence principle as support. However, these measurements don't show a need for the principle, and we'll go over the interpretations now. So some people will say, well, time dilation in a gravitational field, general relativity predicts that time passes more slowly in gravitational and stronger gravitational fields. This time dilation effect is a result of a photon emitted at the top of the tower having a slightly longer time to travel the 22.5 meter distance than to the bottom than photons emitted from the bottom going to the top. Gravitational redshift, according to general relativity, photons lose energy as they travel, as they escape the gravitational field. This results in a shift in the wavelength of the photon to the longer wavelength, which causes gravitational redshift. In the Pound-Repka experiment, photons emitted from the bottom of the tower experienced a gravitational redshift compared to ones coming from the top going to the bottom. And then the equivalence principle, the gravitation equivalence of gravitational and inertial mass. The equivalence principle states that the effects of gravity on an object are indistinguishable from those of acceleration. The Pound-Repka experiment provides evidence for the equivalence as a decrease in wavelength of the emitted photon from the top and bottom, blah, blah, blah. Okay. So their first paper that they published was titled The Apparent Weight of a Photon, and it was inconclusive, and the results drawn, forgot to put it in the slide. Their second paper was this one titled The Effect of Gravity on Gamma Radiation by Pound-Repka, or by Pound and Snyder. So this is basically the same experiment, but slightly taller. And the conclusions drawn from this experiment are: it is not our purpose here to enter the many-sided discussion of the relationship It is not our purpose here to enter the many-sided discussion of the relationship between the effect under study and general relativity or energy conservation. It is to be noted that strictly no relativistic concepts are involved in the description of the effect as an apparent weight of a photon is suggestive. So that's in reference to their previous paper. Then I guess I'm gathering from this that their paper was like being used to, support relativity theory, and they were like, well, we're not even here to talk about that. We're just trying to figure this shit out. This is what we got. Take it or leave it. So then his closing argument: the velocity difference predicted is identical to that which a material object would acquire in free fall for a time of equal flight. So he's basically saying that, well, I'll get to the end here, and then we'll recap. The view that the local timescale depends on gravitational potential appears to require a coherent source for confirmation. The present experiment is unable to distinguish between frequency change and velocity changes. For example, it appears that that it appears as if an experimental comparison of clocks at different potentials would make a useful complementary contribution to the overall status of the theory. So, in conclusion, Pound-Rebka and Pound-Snyder can't distinguish between the effects where the photon is changing wavelengths due to a gravitational field and all that, or if it's changing due to just relative motion. So a null result, if you will, an actual null result. Null result. Examining the three interpretations that are put forward as proof, although the published works of the men who conducted the Pound-Rebka and Pound-Snyder experiments explicitly stated that their results cannot distinguish between frequency shift caused by a gravitational redshift in which the photons would be altered due to the curvature of space-time as it climbs out of the gravitational well, or the velocity shift caused by the photon experiencing a downward acceleration of 9.8 meters per second squared. And same thing going up and down as if it's resisting 9.8 meters per second squared. So the big one that people go with to say that this theory or that this experiment supports relativity is time dilation effects. So when you apply time dilation effects to what was measured, so this is just a quick recap of what's going on here. So the effects measured in the experiment are 2.5 times 10 to the minus 15. That's the range of which they were able to make measurements in. And if you were to apply time dilation effects, you would get effects in the range of 2.17 times 10 to the negative 21. So there's a magnitude difference of 1,000,000 there. So like the time dilation effects don't explain it. So what they basically say to explain it is they say that due to time dilation, this is emitting photons faster than the bottom one is emitting them. It's emitting them slower, and it's giving the appearance of that, blah, blah, blah. And then they do the math, they get this result, and they're like, well, time dilation, even though it's not physically represented in the experiment or within the measurements of the. So afterthoughts on phase shift, so spectral shift. The Stark effect, electric fields such as charges in the environment, currents flowing through the conductors of equipment used to make detections, and the measurements of the photons can produce redshift via line splitting in the absorption lines. And the Zeeman effect, same thing, but that's with magnetic fields. And then it goes on, and then we got the reason for the split is that the electrons changing shells move faster if they are going with the electric or with the field than if they're going against it, right? And that's basically it. So since these photons could be traveling in any direction, an observer at a distance will get both varieties and thus a single emission line. Yeah, so this is just going into detail on how it splits how the emission line splits can happen due to the observations taking place in a gravitation or in a electric field or a magnetic field. So this is Ken Wheeler on electromagnetic retardation. Ken Wheeler demonstrating magnetism as a physical mechanism for phase shift in light and the effects of relative motion. When light travels through a medium with a refractive index different from that of air or a vacuum, it can experience electromagnetic retardation, which causes the interaction of light with the electric or magnetic fields of the medium, or which is caused by that interaction of the mediums, which can lead to a frequency or wavelength change in light, which results in phase shift. So when a magnet is placed over a ferrocell, or I'll just show you the video. So this is a quick demonstration. This will be like a 2-minute video of Ken Wheeler demonstrating relative motion redshift and the Zeeman effect. So when that guy asked earlier about what could cause redshift and stuff, this a magnetic field, all that kind of stuff.
Now.
So, and if you don't agree with what Ken Wheeler has to say about how a magnet works, that's fine. Just tune in at the part where he talks about the relative motion, because that's where he really nails it.
This is red and this is blue. But how can I shift that? Relative motion 2, the disparity of the electricity, i.e. light, which is a coaxial circuit, transverse electrical magnetic, longitudinal dielectric. Let's show you phase shift. Now look closely and I'll explain it. You see how this is blue now? As it was approaching, it went to blue shift. If I move it away, let's just look at this one pole only. Let's ignore this pole over here, okay? You notice that this red shifted now? Let me move this closer to a person over here. Let's say there's a person on a little planet over here, and this is a star. Okay, now it's red shifted. Let's move the star closer to this person over here. You see how this blue shifted? Let's move it away and watch this blue, which is bluish green, but it's still blue shifted, turn to red. Red shift. Blue shift. We're only looking at this pole over here. A second. I think I had a little power outage there. There we go.
Is Doofus in here? Yeah, Doofus. It's not that the light's bending. It's retarding the wavelength as it's going through the field, and going with or against the field can produce different splits. That's what we're talking about.
Blue shift, red shift.
Shit, I fucked it up. Sorry, 1 second.
Do with space, blue shift. So orientate my magnet exactly. Okay. Let's wait for it to appear. There we go. Let's take only a look at this. Blue shift relative to this person over here. Let's say this point over here. Blue shift, as it moves away relative to this point, we have red shift. You notice how it shifted to the red. Now watch it shift again. Remember, only looking at this pole on the right side of my finger. Okay? Red shift, blue shift, red shift.
All right, so that's pretty much all we need to know from that. No, Doofus, we're not discussing the directional change of it. This is different from that. This is a shortening of the wavelength as it goes through the field or medium. So electromagnetic retardation. Even with no medium, the light is still spectrum shift due to the wavelengths being retarded from the magnetic field. If we live in a giant magnetic field, like the Earth's magnetic field, for example, it would be extremely difficult to make relativistic a distinction between relativistic effects and electromagnetic effects. And then there's also the Stark effect, which is with electric fields. So all the equipment that they use to measure these things can also produce those. Not an LED. Dog, I know. We'll get to that in a minute.
Don't worry about Doofus. I recommend.
Yeah. Okay, yeah, because it's not even what we're talking about, and he's like super hyper fixated on it.
Yeah, ignore him.
Okay, so this is hey, look, it's you. Here's Shane St. Pierre from ADL explaining the significance of Earth's magnetic field and how it's obfuscated. We'll play a little bit of this. It'll be relevant when we cover the what's it called? The Heffel and Keating experiment.
Do a quick little recording on this magnetic field map, right? So it's supposedly the magnetic field is the covered magnetic declination all of Earth. Here it's -10, -30, sort of. This is the map that they give you, and then this is the map converted to AE map that I had done, and it puts it off the coast of Australia, right, where they converge. But that's not.
All right, so quick recap. This is what they show us how Earth's magnetic field works. And this is what's actually going on from Bob Wynn's this rotation. So this rotating magnetic field here is what all these lights and everything is going through, and all of that can produce all the spectrum shifts and everything that that's used to support relativity theory. So the translation of motion via translation of motion from Earth's magnetic vortex or the ether, whatever you want to however you want to look at it. So the translation of motion. The physical mechanism for the translation of motion comes from the 8 kilometer per second drift from the Michelson-Morley, which is further backed up by Dayton Miller and 30 years of his repeated Michelson-Morley test. And the data was analyzed by physicist and Nobel Prize winner, award-winning economist Maurice Elias, who did a statistical analysis on Miller's data and found that his results were not due to temperature or instrumental error, and that Miller had detected a gradual change throughout the year, and that the fringe shifts reached their minimum and maximum dimensions right at the equinox, and and this is a direct refutation to relativity theory. Supposing a gradient in the motion of the medium, the translation of motion from the sky would produce a Coriolis effect, i.e., tropical storms rotating in certain directions respective to where they're at on the plane. Yes, so standard atmospheric pressure, i.e., the uniform distribution at the surface decreasing as with altitude, would provide the mechanism for the motion of gradient that's being translated to the surface. And aether is physical mechanism. We don't know, because the people will say like, well, how does the ether work? How does it propagate through? Like, we don't know, how the medium propagates, but basically the way that they used to think of it was basically how sound waves propagate. It's a perturbation in a background medium that allows the wave to exist, basically. So without the medium, there's no wave, essentially. So the Pound-Repka conclusion. The well-established phenomenon of Doppler shift due to relative motion has been confirmed numerous times, through various physics or through various experiments in physics. However, attributing the redshift and blue shift by the Pound-Repka and Pound-Snyder experiments as due to gravitational fields in space-time curvature negates the validity of Doppler shift and instead relies on the equivalence principle, which lacks empirical verification. The principle is frequently imposed as a philosophical assumption prior to conducting experiments, which override the results, and then people will make post experiment corrections to bring things in line with relativity theory, which we'll see later on, shortly here. As seen, relativistic enthusiasts will interpret an experiment in any way possible to support relativity theory, up to and including ignoring the known factors that will affect the measurements and the experimental results, and even outright ignoring the cause of the phenomenon, Doppler shift, etc., and attributing them to bending and warping and stretching of space-time, a concept that has no physical meaning and is only expressed mathematically as a metaphysical solution to observable phenomenon, space-time contraction or expansion. To this day, no terrestrial experiment has ever been done that provides proof that space-time is a physical mechanism, or that it can expand or contract, or that it causes phase shift in light, or that it interacts with or that gravitational fields interact with electromagnetic energy at all. And this is, what was this from? I'm not sure what this is from, but we'll just read it anyway. I'm sure it's important. Considering the weakness of the present experiment, considering the weakness of the present experimental support for the invariance of C, the fact that the observations of moving sources cannot discriminate between special relativity and the old ether hypothesis is the absence of speed of light measurements, which moving detectors, and the lack of experimental validation of the equivalence of the source and observers' motions, doubts, and the interpretations of the classical ether drift experiments concerns about the applicability of the modern isotropy experiments, and the fact that all of the unambiguous tests of special relativity in the photon sector have produced no results. It cannot yet be claimed that the local Lorentz invariance of C is convincingly validated by observations and experiment. And that was from a paper. I quote the guy later. I'll get you, if you were interested in this guy's paper. He goes over 5 predictions of the photon that were supposed to come out of relativity theory, and they haven't, they haven't revealed themselves in any meaningful way that can be distinguished from previous theories. So the whole idea of pushing the space-time curvature stuff forward is under the guise of like, this is the only thing that explains it. This is all we got. This is the best. Well, there's other stuff that explains it. It's just that nobody cares. They're really dead set on, pushing. They were dead set on pushing relativity theory forward, and once it got a foothold in, everything suddenly is proof of relativity theory. The sun came up today, proof of relativity theory. So that's where we're at on. So that's where we're at on that. Heffel and Keating time dilation. The Heffel and Keating experiment was an experiment in physics conducted in 1971 to test the predictions of Einstein's theory of relativity, specifically to test the effects of time dilation and gravitational redshift. In the experiment, atomic clocks were flown on commercial airlines around the world in opposite directions. And the and the times measured by the clocks were compared to a reference on the ground. The result of the experiment showed that the clocks that they had traveled on the planes had experienced small but measurable time dilation effects in agreement with the predictions of Einstein's relativity theory. Very nice. So this is from their first published paper in 1971. And basically, they had all these predictions for how the clocks would go out of sync, because these clocks naturally go out of sync, and when they're in motion, especially, they go out of sync. So they had these predictions so that they could keep everything in line and get a meaningful extrapolation of data out of it. And on their west-east flights, it got out of sync to a degree that wasn't in line with anything, so they couldn't really get any meaningful stuff out of that. Same with the Western flight, and they didn't do. We'll get into that in a second. And so their results here, which is covered from this guy's paper, they didn't give results agreeing with relativity. So the predicted amount was 43, or on the eastward trip was going to be 43 nanoseconds. It was going to lose 43 nanoseconds plus or minus 23, and then on the westward trip it was going to gain 275 nanoseconds plus or minus 21. That's what they predicted using relativity theory. Their first measurements didn't give relativistic results. In a second paper they published the following year, they gave results in agreement with relativity theory, and they state in their paper that they made post experiment calculation corrections and stuff like that. So they, quote unquote, accounted for a bunch of factors and stuff and brought everything back in line. In their paper, they did not, however, include what they changed or how they derived their newfound agreement with relativity. But the paper that I took this little excerpt or this little graph from, that guy got the same results, just like reverse engineering and making up his own math, so to speak, and he got the same results. So even if you don't know, even if you don't know all the factors, you can still bring the results into relativistic predictions by just changing it. So it should be further noted that they declined to do a north-south circumnavigation, and they didn't say this, but I'm assuming that the best argument that I could come up with is that they would just say that the magnetic field would be too strong, and it would impact the results too greatly, because they said that they triple shielded the clocks to prevent electromagnetic retardation and stuff like that. But even that wasn't good enough. So I'm assuming that if they were going to do a north-south, that's what they would say. Or as us flat earthers would say, it's because certain north-south circumnavigation is impossible. And if you were going to do these readings and get this data and stuff, wouldn't you want to get north-south circumnavigation? If it's if that data is verbosely superfluous, let me know why, because I would like, I think it would be cool to have that data, even though it wouldn't serve any purpose. So anyway, Heffel and Keating conclusion: extraordinary claims require extraordinary evidence. The evidence and interpretations from the Heffel and Keating experiment is anything but extraordinary. You can approach the results of the experiment from various angles to show the so-called relativistic effects attributed to it can be accounted to within the confines of natural process, electromagnetic retardation, relative motion, because like I said, the clocks naturally go out of sync. I mean, this whole idea that so like just think about this. So each clock experienced relative time dilation to each one of the clocks. Like it's so insane to go down that road. So in conclusion, this is, it didn't give any meaningful result to time dilation effects, which is basically just applying a Lorentz transformation to the time coordinate in the coordinate system. So it's a purely mathematical concept. It's not a physical one. Like no one out, like the whole, yeah, anyway, you guys get it. So gravitational waves, moving on. Gravitational waves. Oh, I'm sorry. Does anyone have any questions for the stuff that we just covered? before we move on.
Yeah, I'd like to request you to use the phrase superfluously verbose more often.
Dude, I really like it. It's rolling off the tongue now.
I mean, it's adeptly descriptive of exactly what you're talking about, so it's definitely on point.
Yeah, for sure.
Be, be, because I have such a problem with Ken Wheeler,
Mhm.
just in general for everything. For the experiment that he quote unquote did or validated,
Mhm.
is there a repetition of that, or is the only source Ken Wheeler?
No, that's the Stark effect. That's exactly what the Stark effect does. So if we go back to the definition, like this, I forget when the Stark effect was discovered. I think it was before Einstein's time, so it was like early 1900s. They knew that magnetic fields would do all that stuff. So Ken Wheeler doesn't even know. I asked him on his stream a while back about the Stark and Zeeman effect when I saw that video, and he doesn't even know what it is. So he doesn't. So like even though you don't like him or whatever, totally fine. The demonstration is completely solid, and that's a well-known effect. The Stark effect and
Right, right.
the
The
Zeeman effect.
splitting,
I'm sorry. Go ahead.
yeah, the splitting of spectral lines, but not the shifting like a red shift, blue shift. Those are movements, not splitting. So that's why I'm asking. Other than Ken Wheeler, as far as experimental data for backing up the shifting, is there anything else?
Other than the wavelengths of light traveling through the medium, got retarded. Other than that, like I don't know, that produced the effect that you see. That produced the shift. Does that make sense?
Well, I wouldn't call those the same thing.
Oh,
The if you split something into a bunch of spectral lines versus you have spectral lines and everything shifted the same amount in one direction or the other, I wouldn't count those as the same thing. Do you know what I mean?
yeah. So you're talking about like the emission lines versus the actual spectral shift itself or color shift itself. Is that what you're talking about?
Like the shift, right? Yeah, yeah, yeah.
Okay. Yes, I see what you're saying.
The phenomena may be a thing, but
Yeah.
again, I just have such a hard time with Ken Wheeler that I would just need someone else essentially,
Yeah. No, it's
and
all
then
good.
obviously,
Have you
yeah.
have you ever heard of Fractal Woman? She has a really good series on Ken Wheeler's work, and because you know how he does like say a bunch of words that no one knows what the fuck they means, and then he acts like people should just know. But like this woman went through his work and studied it for like 2 years and kind of learned it, and has like a really good video series presentation on it where she kind of goes over everything. If you're interested in learning more about that in terms of like the terminology
Just,
and what he says,
So it took this woman a year to translate Ken Wheeler's information into understandable words in English.
2 years.
We should just watch her instead of Ken Wheeler next time.
Yeah, I mean, I've been watching her. She's pretty dope. I've only seen like 3 videos so far of it, but it like the core like how he's like what does he say about the bang and how it's like the 0 point potential or whatever is the background that the magnetic source comes from and that kind of stuff. Like she kind of the videos that I saw so far, she kind of goes uh into describing what exactly that means, and it makes much more sense coming from her than how Ken talks about it. So if that helps with it, I can link you that if you wanna learn about that. But anyway, we're gonna go ahead and move on to gravitational waves if there's no further questions. All right, gravitational waves. Gravitational waves are ripples in the fabric of space-time caused by collisions of massive objects, in this case, black holes. They were predicted by Einstein's theory of general relativity in 1915, and they were finally observed and detected in 2015. I think it was 100 years to the day by LIGO, which is a laser interferometry gravitational wave observatory. It's basically a big Michelson-Morley device. The detection of the detection provided direct evidence for the existence of gravitational waves, confirmed a key aspect of Einstein's theory. The LIGO is designed to detect gravitational waves. It consists of 2 detectors, one in Hanford, Washington, one in Livingston, Louisiana, which use laser interferometry to measure extremely small distortions in spacetime caused by passing gravitational waves. The laser shoots a beam down a long tube, and the warping of spacetime caused by the passing gravitational wave we'll change the relative distances between the beams of light, causing a detectable fringe shift pattern. And then by comparing the fringe shift pattern with the projections of what the data sets say that Einstein's would predict, they analyze and see if they can detect the gravitational wave. So this guy is giving a press announcement for the discovery of GW150914. This is the gravitational wave detected in 2015, I think it was. So this is their press announcement.
Ladies and gentlemen, we have detected gravitational waves. We did it.
So there's the press conference of gravitational waves. On February 11, 2016, the LIGO Scientific Collaboration and Virgo Collaboration announced their first confirmed observation of gravitational waves colliding from black holes. The gravitational wave signals observed by LIGO's twin observatories on September 14, 2015. This confirms a key prediction from general relativity, and gives the first evidence that black holes exist and that they can merge. This is before they had a quote unquote picture of black holes. So this was like their first big win or whatever, because the resulting gravitational wave came out of predictions made by using the Kerr metric, where two rotating black holes, coalesce in space. They give each other a little kiss, and then gravity waves ripple out from that collision. So this was a big thing for them, and then like an indirect confirmation of other parts of the theory and things that have been derived from the theory, etc. So this is integrity issues at LIGO. I'm not going to waste any more time than what's needed on this subject. We have no way of authenticating the data that they're analyzing. This is an article from their website, from LIGO's own website. The collaboration knew the detection could be a blind injection, a fake signal added to the data without telling the analyst to test the detectors and their analysis. Nonetheless, the collaboration proceeded under the assumption that the signal was real and wrote and approved a scientific paper reporting on the groundbreaking discovery. A few moments later, according to plan, it was revealed that the signal was indeed a blind injection. While the scientists were disappointed at that their discovery was not real, the success of the analysis was a compelling demonstration that the collaboration's readiness to detect gravitational waves. So a really positive spin on the fact that they just rickrolled everybody that works there, and none of them could tell that the data wasn't from an authentic gravitational wave, because they have nothing to compare it to. It's the equivalent of trying to teach an AI how to read license plates, that are like obscured, but not giving them license plates, that are in clear view so that they can, distinguish the alphabet and that kind of shit. So it's just really crazy. So basically, a more in-depth story on this comes from this website, which is I have linked, or you can do on your own time. But you can pull this link up, and basically, a like secret team, so to speak, was given access to their computer systems and everything, and they they did this blind injection of data, and everyone was like, "Oh, ladies and gentlemen, we did it," and they went through that several times, and they don't even know themselves, basically. And furthermore, all of their detections happen under precarious circumstances. So their first detection that didn't get a lot of coverage was an extremely weak signal compared to the standards of whatever they say that they have. But they went ahead and announced it. They gave a positive confirmation off of that, and then on this GW150914, the system wasn't even fully operational. They were doing maintenance on it, and it was rebooting. And before it was fully operational and completely rebooted and everything, the fail-safe system that like helps prevent false positives from being detected wasn't online when they got this detection. And they were about to, they wrote a scientific paper about it, and they were about to publish it and go ham, and they were all super excited. And then this guy had to come down and tell them, "Hey guys, it was just a prank." Singularities and black holes. Oh, I forgot about this. So this is to give you go through this example, graphing the numbers between 1 and 2 and not using whole numbers is, it gives the concept of this line, goes to it goes to 0, but it never touches this, right? It never hits 0. It just goes on infinitely, never touching. So you can count any amount of numbers between 1 and 2. Yeah. So there you go. You get it. So that's basically the concept of a singularity, and that's what a black hole is built upon. So I don't have the actual slide to further build that in, but just imagine the distance between this top line and this bottom line, right? So they say that the distance between this has, this crazy gravitational force, and that's what creates the black hole. Like, this is the singularity. This is a mathematical concept. It doesn't have gravitational fields. It can't suck in light or any shit like that. It's purely a concept. So we'll move on from that. So any questions on the gravitational waves? That was a quick one, because I know it's going long, but it's gravitational waves are dog shit.
So do you think that the people who built the LIGO know that there's no detectable gravitational waves, and they're just like stringing these poor scientists along, or you think they all believe in it too?
No, of course not. This is like the mainstream religion, dude. Like, if you got hired to build a big Michelson-Morley thing, like, you're going to be like, oh, this is dope, because it all goes back to reifying relativity theory. So of course you'd believe in it. Like, you wouldn't have to get people in on it. You would just have to propose the idea to whoever's in charge of, finding or, approving the project and all that shit. And they would just build this thing, and it would, and they would just be doing their thing. And when they don't get any detections, that's when they would get suspicious that there aren't any gravitational waves. So they come up with this story where they're like, all right, guys, we're going to have these people inject blind data in. You guys analyze it. We're going to see what's what, see if you guys can figure it out. Like, the whole thing can unfold itself without really anyone knowing.
So when you say that there's like a prank going on, why do you use the words prank? What do you mean by that?
Oh, it's just humorous because it doesn't exist. And that guy, the head guy at LIGO, per the article, told them that that the detection wasn't real. So it's like, prank is just kind of just a joke.
Gotcha.
It wasn't meant like this guy came up with an elaborate prank to prank his colleagues. It's just like colloquially saying, fool me once or whatever. All right,
Gotcha.
so we'll move on with experiments involving light. So this is to cover. Actually, we'll move this to the back. So this is experiments involving light. So Michelson-Morley and ether. Preface: the Earth is experiencing 4 or 5 different vectors of motion, ranging from hundreds of thousands up to millions of miles per hour. And all these light experiments are only concerned with the local motion, Earth's daily rotation, or their orbit around the sun. These are the smallest velocities compared to the others. In other words, they're only concerned with relating the motion of the sky to Earth. Hang on one second. Yeah. Oh, sorry. The experimental data recorded from Michelson-Morley, continued by Dayton Miller, shows an approximate 8 kilometer per second drift. The only physical, or this is the physical mechanism for our translation of motion claim. This confirms an absolute reference frame for the propagation of light, and we'll just read this real quick. Actually, will we? Yeah, we will. It is widely believed that all the earlier ether drift experiments, e.g., Michelson-Morley, 1887, Illingsworth, 1927, Kennedy and Thorndike, 1932, and the Jews, 1933, all produced no results, although Miller, 1933, insisted that he consistently obtained 8 kilometer per second drift velocity over a period of 30 years. So the homie did 30 years of experimental evidence, getting the same results, and that change in correspondence with the equinox to the exact day, or with the equinoxes to the exact day, reaching their maximum dimensions on the shifts detected. real quick. Over a 30-year, his claims were later discredited by Skankland, his former student, in 1955. So this guy was hired to discredit Miller's work, and he would actually work with Miller. So it's kind of fucked up that he went ahead and just undermined his 30 years of work to for no reason, like he knew. Anyway, Michelson-Morley, 1887, also reported a net 8 kilometer per second drift in velocity, which was widely interpreted as the upper limit and dismissed because it was much smaller than the expected 30 kilometer per second orbital drift for Earth. However, Consoli and Costanza in 2003 recently pointed out several of the well-known ether drift experiments actually produced small positive drift velocities. They reanalyzed the original results from the Michelson-Morley experiment, Illingsworth and Miller and the Jews, and correcting for a Fresnel drag in the experiments, experiments medium, i.e. helium, air, rough lab vacuum, and then the context of Lorentzian relativity, obtained a corrected drift of 240 plus or minus 36 kilometers per second from the 4 experiments, which corresponds closely to the 230 kilometers per orbital velocity of the sun around the galaxy. Comparable results and conclusions have been presented by Manera in 1998 and Cowhill and Kiddo in 2002. These analyses suggest that the ether drift experiments may in fact show evidence of an absolute reference frame for the propagation of light. So this whole thing where they're like, oh, Michelson-Morley, doesn't prove anything. It didn't, the detection was 0. Well, it wasn't actually 0. They expected that the Earth was moving through the ether, chasing the sun or whatever, and that was going to give them 30 kilometers a second. They got an 8 kilometer per second detection, and this was repeated for 30 years by Miller, who lost my train of thought. So if you're one of these people that's like, oh, they didn't detect anything, no result, blah blah blah. Well, when they apply different mathematical corrections to it, they're trying to co-opt it into saying that they detected the vector that's us moving through the galaxy. Like, so either they detected it or they didn't. You know what I mean? But now they're trying to flip flop. They're playing games. They're doing so when you add these corrections from 8 kilometers per second that to get a 230 kilometer a second, it's just like what are we doing here? We'll continue on. Michelson-Morley, linked contraction, and imposing math on reality. Linked contraction is invoked by special relativity to explain why there is a fringe shift pattern detected consistent with 8 kilometers per second rather than the predicted 30 kilometers per second. By all accounts, the results of the test meant either the Earth isn't moving or that there's no ether. They decided to go with removing the ether and using a Lorentz transformation to mathematically imply that the apparatus used in taking the measurements physically shrank or apparently shrank. In relativity theory, the motion of Earth is relative and there are no privileged reference frames. Per its first postulates, an observer on Earth can choose any frame of reference in which to describe the motion of the apparatus to create the illusion that the laws of physics are the same in all inertial reference frames. The use of the Lorentz transformation using the Lorentz transformation, you can show the amount the apparatus's length would have had to contract by to give a result not matching the predicted 30 kilometers a second, and then use that explanation to co-opt the Michelson-Morley experiment itself, claiming that the speed of light is constant and that light doesn't need a medium, as a medium would cause a variable speed of c. Because of this relative link contraction and dilating of physical reality, relativity theory is entirely dependent on c, the speed of light having an absolute speed so that it can be used to measure everything else relative to it, since in relativity theory, length contraction time dilates. The speed of light in a vacuum provides a new unit of measurement to measure time and distance within space-time geometry. To quote Louis Essen, the contraction of length and time dilation can now be understood as representing changes that have to be made to make the results of measurements consistent. There is no question here of a physical theory, but simply a new system of units in which c is constant and length and time do not have constant units, but have units that may vary with v squared divided by c squared. Thus, they are no longer independent, and space and time are intermixed by definition and do not result as some peculiar property of nature. So there we go, from Lewis Essen, who created the atomic clock, came up with all that. He was super into relativity, and then he realized it was, then he had a real change of heart later on after he retired and started looking into it. Him and another guy named Peter Beckman, who was a PhD, professor, teacher, and all that kind of stuff, taught relativity theory, ended up starting a magazine together called Galilean Electrodynamics, where they just kind of went over relativity theory and everything that was wrong with it and just kind of body bagged it. So that's a quote from Lewis Essen, who people will now say, because of his turn on relativity theory, he didn't understand, he's discredited, et cetera, et cetera. Even though he made the invention that quote unquote was used to measure time dilation. So if anyone understands this shit, it'd probably be this guy. If C were, so we'll just move on now. If C were ever shown to have a variance, or that there would be an ether detected, an absolute reference frame, that this would serve as the new absolute reference frame and it would falsify relativity theory, because it would show that the postulates upon which the theory is based on are false in nature. The reason there can't be ether in relativity theory is because it would cause a variance in the propagation of light, changing its speed. Quick reminder on the postulates of relativity. All inertial frames are equally valid, and nothing can exceed the speed of light in a vacuum. When we are asked about the physical mechanism for the translation of motion, or a translation of motion from the sky to the earth, or what's the physical mechanism of propagation of electromagnetic waves through the ether, translation of motion. I kind of covered this earlier, but this was in relation to the ether spinning over, the ether or magnetic field, whatever, spinning over top of us, and that causing, a Coriolis effect, so to speak. That's how that would happen. That would be due to the supposing of the motion, a gradient in the motion of the medium. So the altitude, the air pressure. So as the altitude increases, there's less air pressure. So the spin of the vortex would at a certain distance away from the source of it would start getting a counter rotation, because it would be able to affect it less. You know what I'm saying? So that gradient would provide an alleged Coriolis effect for like tropical storms, that sort of thing. Kind of give an influence on the direction of that sort of thing. Ether as a physical mechanism, we don't know how things propagate through it. But before the ether was fundamentally abandoned to perpetuate fraud using physically meaningless equations, there were multiple mechanisms proposed, and the etheric medium acting in accordance such as the etheric medium acting in accordance with how sound waves act with air molecules. The sound waves interact with the ether, causing it to vibrate and oscillate as the waves propagate. This is similarly to how the exchange of energy between air and water molecules. With a sound wave, the ether provided the mechanism for light to spectral shift, cause redshift, and blue shift, and all that. And then to quote Whitsitt, I can wave my hand, but I can't hand you a wave. That kind of goes in how we were talking about propagation of the waves earlier. We're going to get into the photon here at the end. Oh, shit, did it again. So this is Einstein. If Dr. Miller's results should be confirmed, then the special relativity theory, and with the general theory in its present form, falls. Experiment is the supreme judge. Only the equivalence of inertia and weight remain, which would lead to an essentially different theory. Albert Einstein, Science Magazine, and there you go for the full quote on that. So this is why it was important to have Scanklin undermine his former, what do you call it? The guy he was assisting. on his Michelson-Morley experiments, where they were detecting a consistent ether drift that changed um, with the equinoxes. So that would be like, when the sun moves further away from us, it has a further distance to, it has to go faster to maintain the 15 degrees per hour from our northern hemisphere, quote unquote perspective. So that's kind of explaining why there's a increase in speed and decrease in the fluctuation. Like that could be how that's all related. And, proof of that would invalidate relativity theory, because relativity theory ain't about all that shit. Lorentz transformations. Length contraction, also known as Lorentz contraction, is a phenomenon predicted by relativity theory where the length of an object moving at high speeds appears to be contracted in the direction of its motion relative to stationary observers. While it is considered to be a real optical effect today, there has been no direct experimental test or experimental attempts to test its occurrence in nature and how it is observed in practice due to the breakdown of the concept of simultaneity. Initially, it was thought to be a real physical deformation of the atomic lattice structure of solid matter, but this model was later relaxed and only invoked, and only expressed as like an apparent contraction. So like they don't even have a mechanism for contraction. It's all in the coordinate system. It has nothing to do with reality. In short, the Lorentz transformation cannot be measured because it would have already happened in the observer's frame of reference. If you already assume the observers are in motion, you create an unfalsifiable framework or mathematical framework of interpretation, because when you apply the transformation, it explains your presupposition. Any result that disagrees with that can be mathematically explained away via conceptual ideas rather than physical mechanisms. So if it doesn't give, so the Michelson-Morley, gave an 8 kilometer per second projection. Oh, what does that mean? Well, it means we apply transformations to it, and suddenly we can say that it possibly gives a the speed of the Earth as it moves through the galaxy itself, right? So so that's kind of where I'm coming from on that. In short, because the observers are assumed to be already in motion, i.e., the Earth's alleged orbit of the sun, they cannot measure the physical contraction. Instead, they must extrapolate that it has already happened based on the mathematical transformation they apply to use their contradictory observations and experimental results to confirm relativity theory. Belief in the unconfirmable transformation is fundamental for accepting relativity theory. I had some notes here. Let me just look over this real quick and see if these are worth reading. Basically covered that. Covered it all, so good. The Sagnac effect. The Sagnac effect is an observable phenomenon in which the travel time of light is affected by the rotation of the platform. It was demonstrated in 1913 by George Sagnac using a rotating interferometer and has since been used in many applications, including fiber optic gyroscopes. The effect is based on the fact that the speed of light is constant in a vacuum, but varies in a moving medium. When light travels through opposite directions around the rotating platform, the difference in travel time results in a phase shift in the interference pattern. The magnitude of the phase shift depends on the angular velocity of the platform in the enclosed area. So, quick recap here: light source hits the things, gets split, goes in 2 different directions. As the mirror is rotating, each beam of light hits their respective mirror, and the one that's always rotating away from the one beam that's split is going to be, allegedly further. But they should, if light travels at the same speed, and all that shit, it should hit the thing at the same time, but it doesn't. And relativity's explanation to this is that the Sagnac apparatus is a non-inertial reference frame. So the fact that there is a change in the speed of light, they kind of say, oh, it doesn't apply, right? So it doesn't apply to special relativity, so they get around the falsification of it. The reason this conflicts with special relativity is because it shows that the speed of light changes due to a delay set by a background medium, ether, that's independent of the rotating table and mirrors. And here's a cool video by Michael Bodum, who goes over that concept if you want to watch that. And more on Sagnac. The Sagnac effect. While the classical Sagnac effect appears to conflict with special relativity, it is argued that the rotating instrument is a non-inertial system to which special relativity does not apply. An observer viewing the rotating experiment from an inertial frame would be permitted, under the rules of special relativity, to measure relative speeds that differ from c, so that the apparent speeds c plus v and c minus v of the counterpropagating beams in the instrument frame would be consistent with special relativity. However, Wang and others, 2004, thanks Wang, demonstrated that the Sagnac effect in a non-rotating inertial reference frame using a fiber optic linear motion sensor interferometer. They showed that the light travel time in a straight optical fiber in an inertial motion has a first order dependence on the fiber speed in the local stationary frame. Just as the light time in the rotating Sagnac fiber optic gyro has a first order dependence on the tangential rotation of the fiber optic speed. If the Sagnac effect can be produced by inertial motion, then the rules of special relativity would have to be applied, and the linear Sagnac experiment would violate special relativity. And further noted from their paper, which is here in the presentation, you can check it out if you want. In their paper, they the math they use, basically they extrapolated too that this applies to the circular Sagnac apparatus. So the linear one and the circular one both are inertial reference frames, and that violates special relativity, completely destroys it. If you want to see how they did all that, definitely check out their paper. Ives Stillwell, mainstream interpretation. The Ives Stillwell experiment was conducted in 1938 by Herbert Ives and George Stillwell. It was designed to test time dilation predicted by relativity theory, time dilation predicted by Einstein's special relativity theory. The experiment involved sending light waves through a moving glass tube with hydrogen gas. The tube was made to move at high speeds using a motor, which caused the light waves to experience a frequency shift. The frequency shift measured using an interferometer. The results of the experiment showed that the frequency shift of light was indeed in agreement with the predictions of special relativity. Specifically, the experiment demonstrated that time dilation occurs when objects move at high speeds relative to one another. The Ives-Stillwell experiment provided further evidence for the validity of special relativity and helped establish it as a cornerstone of modern physics. So, quick overview. We got the light beam or whatever in a gas in the tube, or actually this one right here in the tube, and it's connected to a motor and track. They move the motor towards the thing that they're projecting the beam onto, and they measure the interference pattern that they get to see if all reference frames are the same. That was related to the transverse Doppler effect, which was talked about briefly earlier in the presentation. This is the quote unquote confirmation of that, so-called. So this is from the paper that I mentioned earlier that I forgot to cite in that one slide, but this Daniel Y. Greasy guy is the guy that wrote that. So anyway, we'll talk about that. His take on Ives Stillwell. Ives and Stillwell, 1938-1941, performed a second-order Doppler experiment, and that was intended to be a demonstration of time dilation. They measured the longitudinal Doppler effect in red and blue shifted hydrogen beta emission lines, hydrogen beta line emissions from hydrogen atoms moving at speeds up to c equals 0.01 times c, simultaneously approaching the receding direction. Essentially, the same effect in neon was investigated by Haivola and others in 1985 and McGowan and others in 1993, but these results and their interpretations are also problematic. While it is true that the observed redshift and blue shifts are slightly asymmetrical in the relativistic case, they are also asymmetrical in the classical Doppler effect for moving sources. Only this second order effect is actually twice as large as the classical effect than it is in the relativistic case. So detection would be easier in the classical case. The existence of asymmetry does not necessarily mean that the observed effect was relativistic. Kundig, 1963, and Hasselkamp, Mondry, and Sharman, 1997, claimed to have directly observed relativistic transverse Doppler effect. However, the results and interpretations of both works are problematic. Kundig's Mossbauer rotor experiment was recently reanalyzed by Kolometsky and others, 2008. Hasselkamp and others did not initially detect the transverse Doppler effect, but claimed the detection after correcting for possible misalignment. Furthermore, it is a little known fact that a classical transverse Doppler effect is observed in acoustics, which would suggest an analog in the classical wave theory of light, although no such effects is described in textbooks. So what he's saying is this experiment that was used to support relativity theory like the Pound-Repka experiment, gives indistinguishable effects from classical mechanics, specifically classical wave mechanics, where they were, saying that light has a medium is basically what they're saying. So all these, supporting experiments and stuff don't actually support relativity in the way that it's like told to us. We're told that relativity only explains these things. That these are mutually exclusive proofs of relativity theory. Not even close. So here's a list of a bunch of different light experiments involving light and frequency shift and all that kind of stuff. Each one of these, requires a different explanation of how light works, how space-time coordinates work, and how it's an inconsistent explanation to how all these experiments work, and some of them even directly contradict relativity theory itself. Sagnac effect, Michelson-Morley, Ives Stillwell, like some that we've just covered. Pound-Repka's in here, I think, as well. The planet Venus not having redshift on it, or not displaying redshift in the light when it goes by the sun, all that shit. So what about the photon? Well, here's three equations that are used to describe the photon. E equals hc times lambda, E equals hv, and P equals h times lambda. So each one of these equations is used to describe the photon in some way. The only one that describes the physicality of the photon, which gives it the properties necessary to travel through a vacuum, are described by this wave equation. So the thing to note from this dual particle, reality of photons and such is that it's actually a particle so that it could travel through space. If it's not a physical particle, it cannot propagate through space. There's no medium for it to propagate, right? But these are all represented by wave equations. These are all wave equations. The physicality of the photon is required for it to propagate through the vacuum, or the physicality of the photon that is required of it to propagate through a vacuum only exists in your imagination. If the conceptual mathematic extrapolation of the physicality and behavior of the photon existed as described by the wave equations, the length of the photon would be directly proportional to the wavelength of its existence. Got it? A photon that exists at a frequency of 3 hertz for 1 second would be 300 million meters conceptually. That would be like saying that the size of the photon that exists for 1 second of a frequency of 3 hertz would be the size of the distance from Earth to the moon, assuming heliocentric mythology is correct about the size and about the distance of the moon from the Earth. And that size is about 384 million meters. So to give a little illustration of that, this is taken from the channel It's BS. This guy has a really cool presentation on it, illustrates it really well. There's a timestamp for it. So if you were to graph this out, right, so at 0 seconds and at 1 second, the wavelength of the photon existing of 3 hertz, so 1, 2, 3 hertz in between the 1 second, and then you multiply that by the Planck's constant, which is the wavefront here. So 3 wavefronts times 3, you would, that's how that would work out for the photon. So it exists, so a frequency of 3 hertz exists for 1 second, and remember the physicality of the photon, applying that to all that because it's all proportional and described by the wave equations. The physicality of the photon would be 300 million meters. You know, it's ridiculous. A mathematical analysis of relativity. Oh, sorry. Any questions before we continue? I think it's all just flurfers here now. I think all the globular that's left.
Yeah, that couldn't handle it. Dude,
Dude.
obviously Doofus couldn't handle it. BioDuel definitely couldn't handle it. He couldn't even listen to you because you mentioned Ken Wheeler. Yeah, no, that was something to that.
I deafened myself for that portion, but it's all right.
Yeah, I mean it's all good, but like I was saying, it is related to an actual effect. If you disagree with how he says the magnet functions, like that's fine, but the effect itself demonstrated is relevant to conversation at hand, and it's an actual demonstration, which should be more important than the things that come out of his mouth, right? Because you can see the thing. But yeah, totally. Okay, so we'll just kind of move on then to the mathematical analysis. So we got more prerequisites, but we're almost done. There's only like a couple more slides left to go. Prerequisites, definitions, and terminology. Covariant, used to describe a tensor that transforms in accordance with the rules of covariant transformations by maintaining their geometric properties when transferred to a new coordinate system, defining them as independent of the coordinate system. Maintaining covariance is a good way to show that your theory is in alignment with the laws and postulates in which your theory was built upon, e.g., the laws of physics being the same in all reference frames, things like that. So if the mathematical structure of your theory to express that postulate, right, that all the reference frames are the same, the mathematical structure that you're using in the tensors described would have to be covariant, meaning when you transfer them, the tensors themselves their properties don't change. So when you transfer, for example, like if you were say you were going to transfer the speed of light, right? That has to be invariable. If you transfer the speed of light to another coordinate system and it's not the speed of light, well, then you're fucked, right? Then that's not in alignment with covariance, right? And this is what the whole mathematical structure of relativity theory is built upon, and we'll slowly get into that, but this is just an introduction into the terminology that's used to describe the equations and what they do and all that kind of stuff. So invariant, a quantity that remains unchanged under a given transformation, example, the speed of light. So speed of light is invariant because when you apply transformations to it, it doesn't change, right? Fucked up again and hit the wrong button. Anyway, so transformations are mathematical operations that maps a set of objects and another set of objects while preserving certain properties of the original system. So, i.e., preserving properties of the original system, maintaining covariance. Tensors, a mathematical object that represents a linear relationship between a set of vectors, scalars, and other tensors. Pseudotensors, a tensor-like object that transforms like a tensor under transformations, but not under other types. So example would be like linear transformations versus a Lorentz transformation, which is a quadratic transformation. So when you apply a quadratic transformation to a pseudotensor, doesn't translate. It loses its physical properties. It changes, requires post-calculation corrections to be brought back in line. And even doing that itself is a violation. Like that itself doesn't even fix the fundamental problem of the covariance violation, because just the fact that it happens in itself means that the mathematical structure isn't covariant and it's not valid. So, but we'll continue. First order intrinsic invariant differentials, a type of invariant tensor that is coordinate dependent and changes under transformations. It is composed solely of the components of the tensor and its first derivatives. It is not derived from the field equations themselves, and it cannot be obtained from second order field equations, which violates the mathematical structure of the theory based on the principle of covariance and the idea that the laws of physics should be the same and independent of the choice of coordinate system. So we're going to get into what this means and how it relates to the pseudotensor here in a second. This is the concepts. Contraction, a mathematical operation that involves summing over the components of the tensor in a specific way to extract information about the state of the system that the tensor is describing. conservation of energy and momentum, a physical principle that states that the total energy and momentum of a closed system is conserved over time. In relativity theory, gravitational fields and space-time curvature tend to infinity, which violates the conservation of energy and momentum. And second-order differential equations, should have moved that up there. Second-order differential equations. A second-order differential equation is a mathematical equation that involves a function, its derivatives, and its second derivatives. Einstein's field equations are second-order differential equations that describe the relationship between space-time curvature and the distribution of matter and energy within it. Curvature of space-time is affected by the presence of matter and energy in the field equation, and the field equations provide a framework for understanding this relationship. So examples of tensors used, this is the Einstein tensor, also known as the space-time curvature tensor. You'll see it in this form, G subscript U and V. And then this is the Ricci tensor. This is R subscript UV. And then the pseudo tensor in question here, which turns out to be a first order intrinsic invariant differential, is T subscript UV. And we'll get into what all that means here in a second. But to give a quick breakdown, so when you do contracting, what you're doing is each one of these subscripts, so the UV on all of these describes a 4x4 matrix system. So two 4x4 matrices that describe any possible location within the space-time coordinate system is kind of how that works. So when you contract a tensor, you impose conditions on these matrices, and that's how you get information extracted about what's going on with the system. Like how is space-time curving? What's the distribution of mass and energy in the system? Are the conservation laws being conserved? All that information is contained in these matrices that, upon contraction, will reveal the necessary information about the system or the tensors themselves. So if you want to do a comparison or an analogy real quick, say I gave you the ingredients to make a vanilla cake, and I said, these are my field equations. Use these field equations to make a cake. So you look at my field equations and you go, okay, these are all the ingredients for the vanilla cake. You mix up the cake, you make the cake, you bake it. It comes out to be a 4-layer vanilla cake. I'm like, great. Now contract that cake and then tell me, and then tell me what that reveals to you, right? So you squash the cake's 4 layers into 1 layer, and when you compress the cake, when you do a little cake contraction, right? When you do a little cake contraction, it reveals that the cake's actually a chocolate cake because one of the ingredients I fucked up, and it wasn't a vanilla ingredient. They didn't have it at the store, so I just kind of made some shit in my house, used some detergent, drain cleaner, Tide, and all that kind of shit, put it in the cake, and it turned it into a chocolate cake. And you only revealed that by contracting the cake. So is that we all on the same page of what's going on here?
That's an excellent analogy, too.
Thanks, man. I came up with it the other day when talking to Jim, and I was like, wow, this is actually amazing.
That is excellent. Well done, Jim. Well done, Alan.
Yeah, thanks, man. Thanks, Jim. So yeah, that's what's going on there with the tensors and all that. And we'll see how this applies. So this was going to be a reference to show what the tensors are on the other slide, but I just included them anyway. So you can kind of ignore what's going on here. So introduction to the issue at hand, covariance, pseudotensors, and the conservation of energy and momentum laws. This is an introduction to the use of the pseudotensor in relativity theory. This is an introduction to the use of the pseudotensor in relativity theory to satisfy the energy and conservation of energy and momentum laws. In general relativity, the field equations are second-order differential equations that describe the curvature of space-time and its effect on the motion of matter and radiation. The problem is that these equations do not satisfy the conservation of energy and momentum laws, which is a fundamental principle in physics. To address this, physicists have tried to define a gravitational and momentum and a conservation law tensor that would satisfy these laws. However, the only known way to interject such a tensor is by using a pseudotensor, because as we were talking about earlier, the Einstein's field equations are second order differential equations, so they can't produce a first order intrinsic differential invariant differential, because that's not derived from second order equations. It's not mathematically possible. So It's a violation of the theory to use this tensor to satisfy the laws, yet they do it anyway and act like it's all good. That's why I was talking about when dude was saying, well, what's up with this experiment here where these guys measured it and using relativistic math predictions were able to satisfy the conditions. The violation of the mathematical structure, this covariance issue and the conservation laws, this renders the whole structure of and the math and everything physically meaningless. It doesn't describe anything. So in the engineering example where they're describing an I-beam, all the math and everything used to describe that has to be derived from the system describing the I-beam, and all the and any stress and all that stuff, put into it comes from the system that it's derived from. So it's physically meaningful. So you can see, if this stress is exerted on this beam, this will happen, right? So when you do that with relativity theory, it doesn't mean anything because the structure that they got to get their predictions and make everything align doesn't satisfy the structure of mathematics that it's supposed upon, and it violates which means that it can't mathematically express the postulates upon which it's built upon, which is all reference frames are the same and all that kind of shit. Because when you use these tensors and transform them, the pseudo tensors that's used to satisfy these laws transform it doesn't keep its geometric properties. It requires post calculation corrections. It requires the use of other tensors that are derived from other tensors. The big issue, like I was saying here, they cannot get a tensor that satisfies the laws from the field equations. But they'll do like weird things. They'll derive a tensor from a tensor that's already been derived. Like they'll just do this like weird thing where they just kind of try to build onto the system indirectly, which violates the structure. It completely renders it just useless, really. Because then you think about it like this, you could say, well, no, the perihelion precession is due to unicorn dust. It's not a vacuum out there; it's unicorn dust. It just becomes a thing where you could say cause and effect relationship is caused by anything using the math, and you don't have to it doesn't have to be represented in a physically meaningful way. So to continue on here. To address this, they tried to do that. In the 1900s, Ricky Cabastro and Levi Civita proved that invariants that are composed solely of components of other metric tensors and their first derivatives do not exist. And what they mean by do not exist is that they do not exist within the system that they're supposed to be describing. So this is really dense. So I'm going to keep kind of repeating it, if you guys don't mind, to hammer it home, because this is hands down like a fundamental thing that's everyone has known for a long time. When relativity theory was coming out, like they've done these mathematical analysis, years ago, and they've known about these problems, and they just ignore them, and they just pretend like it's all good, and the use of the pseudo tensor satisfies it, and the use of these other tensors that they made satisfies it. It doesn't. Completely destroys it. All right. So, and these two guys here are the two guys that invented like differential calculus and all this and the use of the tensors and all this shit. So if anyone knows about mathematical structures and the validity of them and all that, it would be these guys. And then so we'll go on to, this means that the use of the pseudo tensor is not consistent with the mathematical structure of covariance which the theory itself is built upon, and does not provide a satisfactory solution for the problem of defining the gravitational energy momentum tensor. This is a catastrophic failure because the conservation of energy and momentum is a fundamental principle of physics, and any theory that fails to account for it adequately would be considered to be incomplete or inconsistent at best. It is the use of this pseudotensor that invalidates the theory and anything derived from it, including orbital explanations, black holes, gravitational waves, physical or apparent contractions, space-time curvature, and whatever else you think that space-time curvature proves. Anything that's extrapolated from the use of those tensors is physically meaningless. So when they say, oh, we detected gravitational waves. Okay. Is that why you had to do it, under the precarious circumstances every time and be all super weird about it? This is why these things operate this way, because they're theoretical, can't be confirmed, and they just impose it mathematically. So black holes, this is another extrapolation of using the tensors that are in question, and it completely body bags those as well. Literally everything that's derived and predicted uses the pseudo tensor to satisfy the conservation laws, and that invalidates it, because the pseudo tensor itself can't even be derived from the field equations. In conclusion, the failure of the pseudotensor in relativity theory is a significant problem that undermines the very foundations of the theory. Physicists continue to search for a tensor derived from the field equations, and that's a lie. They don't, actually. I just kind of wrote that in to give the Globers a bone. They stopped searching. They can't. It's not mathematically possible. That's why they don't. Anyway, so physicists don't continue to search for a don't continue to search for a tensor derived from the field equations that produce a physically meaningful equation that's covariant with the Newtonian framework or even the framework of relativity theory itself to date, but no such tensor exists. This highlights the fact for an ongoing need to find one and address this catastrophic failure. So to recap, have you guys ever heard Newton's equations reduced back to, Einstein's equations, field equations reduced back to Newton's equations, and that relationship is shows that this isn't a completely new system that overtook everything, that it's more of an extension to the Newtonian framework. Have you guys ever heard that? All right, well, I've heard it a bunch talking to people, and that's what they say. So this is a direct violation of that, because the non-covariance means that it doesn't reduce back to the Newtonian equations. The transformation out of the Newtonian framework into the Einsteinian framework is how they got into this situation where they have to use these tensors that violate the structure of the system that they just transferred into. So there's no reason to even justify applying a Lorentz transformation to the Michelson-Morley experiment, because the system that they just transferred into doesn't satisfy the conservation laws. And when you try to introduce a pseudotensor to satisfy the laws, it breaks covariance with the new structure itself, and it breaks covariance with the Newtonian framework. So it's not even true to say that that Einstein's equations reduce back to Newtonian equations. They don't do it in any meaningful way, right? So that's where we're at with that. We'll continue on. Covariance and pseudotensors. It is important for relativity theory to be covariant with Newtonian mechanics because it allows for the new theory to be seen as a natural extension of the old one rather than a complete break from it. The backwards compatibility with the Newtonian framework means that the new theory can scale upon what's already known and assumed to be fundamentally true on the local level, in regards to physics and conservation laws, that sort of thing, while requiring a new coordinate system to describe cosmological behavior. If Einstein's theory had not been covariant with Newtonian mechanics, it would have meant that if Einstein's theory had not been covariant with Newtonian mechanics, it would mean that it would have meant that this is a completely new theory and it's disconnected from the old theory of the Newtonian framework, and that it cannot be seen as a natural extension. This would have made it much more difficult to convince the scientific community to accept the new theory as a valid replacement of the old one. However, the use of the pseudotensor has led to a controversy over the accuracy of the physical reality it reflects in gravitational systems, particularly in situations where gravitational and conservation is crucial, which is always. While the pseudotensor helped describe the energy and conservation of momentum of gravitational systems, it is not covariant, which means that when transformations are applied to the system, it results in inconsistent results, meaning that the laws of physics aren't the same for all reference frames, et cetera, unless you do post-calculation corrections. It can be argued that Einstein's ad hoc use of the pseudotensor invalidates his covariance with the Newtonian framework and is akin to a mathematical version of a begging the question fallacy or reifying the consequent. Nonetheless, the Lorentz transformation is applied to the Newtonian experimental results results of the Michelson-Morley experiment to join the two theories mathematically. In the context of special relativity, the Lorentz transformation is a nonlinear transformation that describes the relationship between the coordinates of an event in different inertial reference frames. The Lorentz transformation is nonlinear because it involves terms that are dependent on the square of the relative velocity between the reference frames. Furthermore, it is not linear because, the transformation that comes out of, or the tensor that gets transformed using the nonlinear transformation shows that it's invariant. The resulting nonlinear transformation causes the pseudotensor used by Einstein to become non-covariant. The resulting nonlinear transformation causes the pseudotensor used by Einstein to become non-covariant with the Newtonian framework or its own framework. By implication, it would reveal that Einstein's spacetime curvature was a departure from established physics and started a new system entirely not built upon what was already assumed to be valid. In closing, Einstein's transformation used to bridge the framework with Einstein's new framework disconnected them entirely from the established heliocentric lore. Go back to the script. I didn't describe this correctly, and I was trying to reword it in real time so that it made sense. But
I like how you call it lore. Lore is pretty accurate of a term for what heliocentric nonsense is.
Heliocentric lore and heliocentric mythology, dude.
That's great.
And even if it was a so-called script, you can reference all the papers in here and compare them to what's being said, and it will align, perfectly. So, I don't know. Anyway, so we'll move on. Wait, move on way too far. Okay, so in conclusion there, we got a couple more to go through here. So in conclusion, to quote an elegant summary from a paper that's cited on the next slide, Einstein's general theory of relativity links matter and the gravitational field into a single entity, while first is characterized, as in the other theories, by the momentum tensor that is a second-rank tensor. The second is characterized by the curvature tensor, which is a fourth-rank tensor. So we remember back, the Einstein spacetime curvature tensor is what they're referring to here. So this one, all good. And then the second one that they use to describe the characteristics of energy and momentum is a fourth-rank tensor, which, when contracted, reveals itself to be a first-order differential, or if first-order invariant differential, or differential invariant, I mean. So it's not compatible with the field equations that it's supposed to be, in alignment with, because the field equations themselves provided an interpretation of how to interpret the contraction and stuff of the tensors, right? So it doesn't go along with it at all. Due to the different dimensions of the physical characteristics of the gravitational field and matter in Einstein's theory, it follows directly that there cannot be, in general relativity, any conservation laws linking matter and gravitational fields. This fundamental fact, established by Denisov and Lugdanov in 1980 and Hilbert in 1917, means that Einstein's theory was built at the expense of repudiating the laws of conservation of matter and gravitational fields, and the gravitational field is taken together. So this Russian guy, Denisov and Lugdanov, figured this out. Hilbert figured this out in 1917. Like, this is a known thing, right? That they've been working on within the heliocentric mythology, and they can't quite seem to get it right. And we'll get into some of the other tensors and stuff that they've produced, and none of them satisfy covariance or the conservation laws in a meaningful way that it would have to be to maintain to give physical meaning to what they're claiming that the equations represent. We denote from everything except this is a quote from Einstein on how he calculates gravitational fields. We denote everything except the gravitational field as matter. Therefore, our use of the word induces not only matter in the ordinary sense, but also the electromagnetic field. So he's going to go ahead and calculate the gravitational field as matter. The mathematicians and physicists A. Lugdanov and M. I'm not going to bother trying to pronounce pronounce that dude's name. The mathematicians Lugdanov and this guy gave rigorous criticisms of Einstein's relativity theory. Okay, the mathematicians Lugdanov and this guy rigorous criticisms of Einstein's general relativity theory support the view of H. Minkowski that gravitational field is primarily a geometric field rather than a physical one. Einstein himself recognized that in this statement that everything changed except the gravitational field, which can be denoted as matter, including the electromagnetic field. However, within the framework of geometric gravity or general relativity, there is no tensor characterization for the impulse energy of the gravitational field as established by Hilbert, Einstein, Schrödinger, and Bauer in the early 20th century. Therefore, the gravitational field is a metric field without physical reality, and treating it as such violates the mathematical structure of relativity as well. So there's actually a couple different things where they do this thing that violates its own structure. So GUV is the Einstein tensor in general relativity, which is a second-rank tensor that encodes the curvature of spacetime and the distribution of matter within it. The Riemann curvature tensor describes the curvature of spacetime and and is derived from the second derivatives of the metric tensor GUV with respect to the coordinate system and is defined by this right here. So if you notice, this right here has two extra indices on it, which means that it's a rank 4 tensor. So earlier when they were talking about this is a rank 2, this is a rank 4. So this rank 4 tensor isn't derived from the field equations, and it breaks that relationship again. They just continually violate it over and over. Covariance and pseudotensors continued. The issue with Einstein pseudotensor is that it produces an invariant that is a first-order differential invariant, which violates the mathematical structure of general relativity because of the equations of general relativity are second-order differential equations, and the use of a first-order invariant is inconsistent with the mathematical framework. In the 1900s, Ricky Capastro and Levi Civita proved that invariants composed solely of the components of a metric tensor and its first derivatives do not exist. And like I was saying, making a tensor out of another tensor doesn't mean that it's covariant with the field equations that the first tensor was derived from. Since Einstein's use of the pseudotensor is invariant and constructed solely of the components of the existent of these components, its existence is shown to be invalid and validates the mathematical structure. Additionally, the use of the pseudotensor to define gravity or gravitational energy and momentum tensors is not consistent with the mathematical structure of the theory, as there are no invariants that can be constructed using only a metric tensor and its first derivatives that can be used to find a gravitational energy and momentum tensor. While several attempts have been made to rectify this issue, including the Landau, Lifshitz, the Bell-Robinson, and the Bergman-Thompson tensors, to date, no tensor exists that satisfies covariance with the Newtonian framework or the conservation laws or even the relativistic framework itself. And all these papers here are in reference to everything I just talked about here. These last 5 here are like really good ones, really easy to get your head around. So Desanov and Lugdanov argue that the inertial mass defined in the gravitational field argues that the inertial mass defined in the general theory of relativity has no physical meaning. They also show that the inertial mass introduced by Einstein's theory on the choice of a three-dimensional coordinate system depends on the choice of a three-dimensional coordinate system, so it takes arbitrary values. This means that the inertial mass in Einstein's theory has no physical quantity. Moreover, the expressions of inertial mass in Einstein's theory does not have a classical Newtonian limit in the general case of an arbitrary three-dimensional coordinate system, violating the principle of correspondence with Newtonian theory. In contrast, the gravitational mass of the system is well defined in the theory of relativity, and it does not depend on the coordinate system. All right. So, questions about heliocentric mythology, dark matter, and spectra shifts. Since it has been shown that space-time is purely a concept and not a physical mechanism, a question arises about the physical mechanism responsible for the propagation of mass through gravitational and/or space-time curvature. The mechanism must cause mass to accelerate in such a way as to impose a speed limit on something in free space, while enabling it to complete its orbit without any disruption. Without space-time curvature or gravitational fields to propagate through, how can dark matter explain the anomalous gravitational orbital behavior? So, if you're not familiar with dark matter, they introduced it when observations were made of a galaxy that was "quote unquote" rotating too fast, and it shouldn't be able to do that based on its mass, which is calculated based on uh, what is it, the noble ladder and the fucking candle system, where they calculate the brightness of a galaxy and divide it up, and they see how much the stars and shit in it weigh or whatever. So based on this system, which can't possibly be wrong, an observation was made that directly contradicted it. So to explain it, they said that there must have been something, another mass there that doesn't interact with electromagnetic energy, so it can't be seen or detected, but its presence is there, and that's affecting the space-time curvature in such a way that it's causing the acceleration of the galaxy in such a way that it also doesn't rip itself apart or anything like that. Right? So it doesn't have enough mass to hold itself together, rotating too fast, and they just hit your boy with with dark matter. And they say that it propagates through gravitational waves or fields, I believe. Professor Parks, can you give me a quote on that? How dark matter is supposed to interact with gravitational fields, or act on bodies through gravitational fields?
Sure. Dark matter is simply. Oh, sorry.
I'm sorry. Did you catch that? Was that an accurate description of what's going on?
I just popped in, so could you
Gotcha.
go over that again?
Yeah. So we were discussing how space time doesn't have a mechanism anymore or anything like that. So I was going to ask about how dark matter is supposed to interact with objects, right?
Okay.
So, from my understanding, they say that dark matter interacts through the gravitational field, and it doesn't interact through the electromagnetic, spectrum or anything like that.
That's correct. It only interacts gravitationally. It does not interact electromagnetically. It does not interact through strong force or weak force.
Okay, cool. So yeah, everything in that was accurate then. So special relativity was accepted because the Lorentz transformations enabled astronomers to maintain their adherence to the Copernican principle and false axioms regarding the sky and mathematics to deduce the motion and curvature where there is none, without having to admit that their post calculations and calculations are physical, or post predictions and calculations are physically meaningless. And that's the mathematical analysis. That's the whole thing. And we'll read the conclusion real quick, and then we'll do a recap with Professor Parks. How math became reality. Conclusion. In conclusion, the historical and classical experimental evidence put forward as proof of relativity theory does not support the theory, and has entirely collapsed on itself at free fall speeds, revealing it to be a mathematical prank played on us all. In my opinion, there was a deliberate effort to promote the theory of relativity to make it widely accepted. Someone or some group of individuals realized that they could use this framework of space-time curvature interpretation to manipulate the concept of space-time and natural electromagnetic phenomenon by using the space-time metaphors supported by mathematics that are physically meaningless. The term space-time or space-time curvature is misleading, because they're imaginary. There is no experimental proof that the theory of relativity is anything beyond a mathematical framework. Space-time possesses no physical attributes that can distort or alter time, or change the path that a mass or massless object is traveling along. Because of its non-physicality, it doesn't have any curvature to extend to that. So some individuals may think that the theory of relativity has been verified because its predictions have been validated on several occasions. Other concepts like the Lorentz ether theories also produced comparable outcomes. The issue with the theory of relativity is that it employs mathematics to make predictions successfully, but the way it describes time and space is illogical and even goes against established knowledge. The underlying problem arises from the switch to Lorentz's concept of a absolute time and a variable speed of light to Einstein's idea of relative time and a constant speed of light. The Sagnac effect demonstrates that the speed of light can vary based on the observer's position, which can make it appear as that time passes differently. The major difference between the two systems of the Lorentz system of Lorentz's system implies that the stars, planets, and galaxies and other celestial objects are close to us and exist in a denser medium. In contrast, relativity theory is essentially the inverse of the ether theory of a closer and denser medium. This allows for a broader range of interpretations concerning the distances and sizes and the nature of the so-called vacuum of space. This is the reason why mainstream science can state with a straight face that a photon has traveled 13.7 billion years to reach our eyes and has covered a distance of 86,600 quadrillion miles is due to that inversion of the constant speed of light and relative time. Experiments should guide the progression and validation of theories rather than the theories influence the results of experiments, so that the data can be selectively used to confirm the theory. And then all the sources are available in there, and then the ones that I built into the slides that I added after I made the original presentation are just in the slides themselves here. All right, so that's the full presentation. If anyone has any questions, comments, hit me up while I'm here. And then Parks, if you have some stuff you want to talk about, definitely want to get your take on some of this.
Unfortunately, Alan, I haven't had time to really watch through all of that.
All good.
I do have a couple of just overall, just comments from just that conclusion. One, you basically say that relativity is a mathematical framework and can be ignored and such. What makes that different from the ether theory? You'd realize that the ether theory is also a mathematical construct as well, right?
Good point.
In your conclusion, you made some kind of claim that special relativity, special in general, is a mathematical framework, essentially. It's a mathematical tool. Mm-hmm. And the implication is that it can be ignored because it's not physical. It's not real.
Yeah, so the ether stuff all produce things that directly conflict with relativity's postulate about, space-time and infinite vacuums and all that shit. So when I say that it's, a physically meaningless system, that it is, because it doesn't have anything to do with anything in reality. And that can be demonstrated by the lack of covariance with the Newtonian framework, the lack of covariance with the theory itself when they start using pseudotensors to satisfy the conservation laws. So in regards, it's just a system that they can use to describe lights in the sky, because it's essentially a blank slate of interpretation where they have a license where they can swap out tensors, curvature tensors, and express whatever they need to, whatever story they need to tell, basically. And it doesn't even matter if the tensors themselves are covariant with the structure of the theory, because the main ones that they use now aren't, and they don't care. So that's why I say it's physically meaningless. Because if you were going to define a system, like, say, for example, if you were going to use a tensor system to define, an I-beam and what's going on at any particular point in the I-beam, you would have to use physically meaningful equations. You couldn't just, say, oh, space-time is contraction to infinity. Oh, there's an infinite, source of, whatever acting on this. Like that doesn't happen in these equations. This only happens in the abstract framework where you can, make the math say anything you want.
I got a question.
What's up?
Actually, I have two things. So, talking about covariance between Newtonian gravity and relativity, that everything in Newtonian mechanics was either verified or rejected by relativity. But there are things in relativity that don't exist within Newtonian mechanics, because what it essentially is an expansion, right? It didn't kick out Newtonian mechanics. It didn't make it irrelevant. It's basically a deeper comprehension of the observations that Newtonian mechanics makes, right? So instead of just saying mass attracts mass, and that's how it's going to generate this vector and create this orbital path, It's saying this is why it happens, right? The curvature of space-time causes this. And my second thing is talking about using different orders of tensors than the equations you're using in relativity, the differential equations. That's the point of relativity, right? So you're taking tensors in lower dimensions, right? Or as you can refer to them as vectors if you like, of motion, right? And you're using these differential equations to break them up into their constituent parts, or the opposite. And that's why the differential equations, for example, like the Lorentz transformation, are of a higher degree, because you're converting motion within the, well, or you're describing motion within the framework of 2 dimensions or 3 dimensions in a tensor in terms of its 4th dimension, which is time. You see what I'm saying?
Mm-hmm. Yeah, so it's not even the use of the tensors itself. It's the covariance itself is actually violated by the use of the pseudotensor. It's not necessarily the rank of the tensor. It's the fact that when you apply transformations to it, it's not covariant. So the use, and then all subsequent pseudotensors used to satisfy the conservation laws are also non-covariant. So when you say that when you say that it's an extension of the Newtonian framework, it's actually not, because it doesn't transfer into anything meaningful. So when they applied the Lorentz transformation to the Newtonian framework to get to special relativity for Michelson-Morley, they transferred into a system that's not even covariant. So it's not. Yeah, go ahead.
Sorry. So yeah. So you say it's not covariant with what Newtonian mechanics would produce, but it's what's the word?
Well,
it reflects reality.
No.
So
the field. Okay, sorry. Go ahead.
Well, Newtonian mechanics. I know you were talking about a few earlier. I haven't looked into that, but you were talking about how general relativity would predict twice the gravitational lensing of light that Newtonian mechanics would, and things like this. That's the reason general relativity exists, is because there's things that Newtonian mechanics could not explain.
Well, here's where it gets really crazy. I'm assuming you came in late and didn't see the entrance. So the predictions of relativity theory, So the predictions of relativity theory of the greater bending of in arc seconds weren't actually shown. They all gave predictions closer to the Newtonian framework, and all of Cromlin's observations were completely disregarded, so that Eddington could use his 2 photographic plates to support the so-called star displacement. But when that's even analyzed, the only displacement that happens is actually near the solar limb, where there's already supposed to be a medium of plasma or whatever. So this, like the gravitational field in general relativity doesn't just stop at the plasma limb of the sun. Stars nearby should be displaced even to a lesser degree, but they should still be displaced. But there isn't any displacement. And then so when you go on and say, like, space-time curvature describes reality, how so? Because all experimental evidence used to support relativity theory that I went through in the presentation reveals no such relationship where a gravitational field or space-time curvature exclusively or mutually exclusively interacts with light or anything to produce these so-called effects. Like the story behind the mathematics used to describe what's going on isn't real. It doesn't have any meaning to it. Yeah, you may.
Wait, what?
What's up?
I have to say, Alan, you are certainly a student of Whitsitt. And
I don't know what that.
Hold on, I'm not done.
Sorry, go ahead.
I do have to go, but you are really why I'm irritated is because you are the narrative that you were pushing, and it is a narrative, is that we are deliberately, and when I say we, I mean the scientific community, that we are somehow suppressing knowledge, or that we are misleading the people, and that I really have a problem with that. And the other thing that you were completely ignoring is that the Eddington experiment has been done multiple times since then, and is currently going to be done with the solar eclipse in 2024, with using CCD measurements. So you are hanging your hat completely
Can I respond
on
real
the
quick?
Eddington storyline.
Can I respond real quick?
I'm still not done.
Oh shit! All right.
You are basically talking simply about the Eddington experiment.
No,
and
not.
when you talk about
You haven't read the whole presentation, and I just did the whole presentation, which you didn't see. I explicitly cover different observations. This guy, Edward Dowdy, covers multiple observations. Only happens at the solar limb. That's it. There's no Eddington observations. The Eddington predictions didn't even come in alignment with Newtonians. Or, I'm sorry, the Eddington observations aren't in alignment with Einstein's predictions either. So this whole narrative of you're the guy that has the narrative. Don't be mistaken, because there was actually an experiment done, or observations done in tandem with the Eddington experiment, where I got two guys, St. John's and Evershades, where we're doing spectroheliograph observations, trying to get gravitational redshift observations from the displaced stars, and they didn't get any. So there's no cause and effect relationship for gravitational redshift and displacement of stars due to gravitational fields or going along space-time curvature. And I don't like that you're insinuating that being a student of Witsit is a bad thing. I went through all this research, did all this stuff. It's completely contradictory to everything that you say. I have all the sources here, all the papers here. You can read everything I say in this presentation.
What are the control variables?
It's directly It's directly backed up by
Okay.
by what I'm presenting. So when you say you're spinning a narrative, yeah, I'm spinning a narrative, but it's derived from factual things that happened. I'm not just making this shit up. Subsequent observations have been done through since the Eddington one. None of them give predictions, or none of them give conclusive evidence of what you're talking about. None of them. Not a single one. So I'm not hanging my hat on just some shit I made up last Tuesday, bro. Like, I have a lot of respect for you, and I want you to look into this and go through this so we could actually figure out the best possible points of this presentation. And for you to sit there and act like I just made this shit up and I'm just talking that shit, kind of super disrespectful, bro.
All right. When I said you were a student of Witsit, what I meant was that you use certain tactics that Witsit does, such as talking very, very fast, over talking people, and taking offense at things that are not in evidence.
You took hold on a sec. You took offense to me telling
talking over-
you. Yeah, my bad. Go ahead, Parks. I'm sorry. I apologize. Go ahead. You're 100% right on that. Go ahead. Can you stop doing that, Alex?
I did not make the assumption, Alan, that you made this shit up on Tuesday.
Okay. Yeah. My bad, dude. Okay.
I did not. I am not suggesting that you have not well researched this this area. What I am suggesting is that you have not researched this area enough. Now, I will say that you are correct. I have not watched your entire presentation, and these new observations, such as with John Maddox, I am not familiar with. I am familiar.
This is him reviewing multiple observations that have been done. This is another guy reviewing it from the 60s, multiple observations that were done subsequent to the Eddington one. And this is Edward Dowdy, who goes over a bunch of different ones. And he came to the conclusion, the same thing basically that I'm saying, is that it only happens near the solar limb. So come 2024, when that eclipse happens, and it's only towards the solar limb, can we, just like send me a message and be like, hey man, sorry, or something. Because it's going to happen, because it's all that happens.
All right. Can I finish?
Yeah, go ahead.
So, again, over talking.
Yeah, I'm sorry. I don't mean to over talk on you or talk fast. If I lose my train of thought, it's a wrap. I know I just immediately did it to him, but I'm trying to explain it. I don't mean it to be like that. It's a tactic. It's just if I don't keep going, I lose my momentum and I can't get the train of thought back. It happened several times through the presentation. It's just how my brain works, and I'm trying to talk about that stuff. So when I start going over it and I get in a good flow, I'm not trying to do a Witsit, you know what I mean? It's just coming out that way because it's just how my brain works. If I stop and try and do it slower, it doesn't come out right, and I lose track. So I apologize, and I didn't mean to talk over you again. I just don't want to I don't think that's a good criticism. So I just wanted to put that out there before we continued on.
Just an observation he's making, not a criticism of you. I don't believe.
Yeah, all good. Yeah, I'm just letting them know where I'm coming from on that. I'm not trying to like pull a fast one on anyone or anything like that. It's
that's
just
your part.
Yeah. So
stop trying to do a Witsit.
Yeah. So I'm sorry. Go ahead, Parks. Please continue. I do apologize. And just so you know, bro, I do respect the fuck out of you, dog. Like I've been, you're my dude, bro.
Alan, we're good. I mean, I hope we're good.
We are.
I respect you as well. It's just I can DM you about this later
Yeah.
because I do have to go. But
Yeah.
I will. I do plan on watching your entire presentation. I think at least part of it is on your channel.
Yeah,
So
I
I will
just
go.
I'm gonna upload this one because the audio is way cleaner on it. So I'm gonna upload this one. I'll send you a link to it when it's up. And if you want to just start from that one, it'll be way cleaner audio because the other two I uploaded are pretty dog shit in audio terms.
Okay. The last thing I will say, just sort of in relation to this specific topic, is relativity would tell us that does seem to or would predict that the gravitational lensing effect would be greater closer to the sun because you were closer to the central mass.
Right.
The other issue, as you brought up, is the corona. The corona is an exceedingly rarefied plasma. Like, it is ridiculously rarefied to the point that it's barely even denser than dead space or empty space. So the idea, and I could be wrong, but I believe that's somewhat implying that because there is a medium there, it is going to cause the light to refract as we would expect with glass or what have you.
Yeah.
And I can assure you that really isn't going to be.
Yeah, that's
but
interesting. We'll have to follow up on that because that's what this Edward Dowdy guy's whole argument and stuff was. So and he even has equations for his for what happens to the light as it passes through the so-called medium and stuff like that. So it would be interesting to go over that with you for sure.
Okay. All right. Yeah, I will look into Dowdy and see what's going on.
Yeah.
But all right. Yeah.
Oh yeah.
Yeah.
Sorry.
So I was also going to talk about the presentation itself, but that gets into I'm putting my professor hat. But anyway, yeah. Cool. I will check out your presentation when you send me the link. I will check it out.
Cool. Yeah, I'll
I
send
got
it
a question.
send it to you shortly. Yeah.
So a lot of the things I hear about, they go to like Einstein's experiments and this and that experiment. They say, well, it actually proves flat Earth, and here's why. So what I'd like to know is, are there any experiments done to prove the flat Earth ether theory that have gone wrong and got to a null result? Because it seems like when we point to those, that did get null results for Aether and everything, it's somehow used. And the assertion is that science is lying; they're hiding things from me. So I'm just wondering, are there any experiments that are done for flat Earth ether that come up with no result, like many of the published ones for science have? And then you guys go like, oh look, they tried this and they couldn't get it right because they don't know how to science right. So I'm just wondering, is there anything like that for your position?
You mean published null result ether experiment test?
I mean, like anything for like flat Earth. Are there any experiments done to show the flat Earth that were negative results?
In regards to what are you
Or is
talking
everything
about?
a positive?
What do you mean? I don't. What's he talking about? Interpret.
He is referring to experiments that are attempting to discover something related to your topic via the ether, and he's referring to are there any experiments where the results that you were looking for were not what you wanted?
Let me get this one for you.
Oh, you mean like did we test for ether and then confirm space-time curvature? Is that what you mean?
Not specifically, but if there was an error in it.
Oh,
I think that's what he's asking.
I don't know, man. I'm sure there are, bro. So I'm sure there are.
It just feels like anytime that there's like a misstep in science or they didn't get the result they were thinking they'd get, that's somehow a negative towards the scientific method. Or
I got you. So let me cover the narrative again real quick, right? So all these let me cover the heliocentric mythology. Right? So hang on, what's this fucking dog? Hey, buddy.
He's like, I need to go out and a treat and near attention right now.
Yeah, all of these things at once. So hold on, he's going to do it again. Hopefully, God. Okay, so in heliocentric mythology, right, there was the Copernican principle, which was saying, hey, we're in motion and all that shit, chasing the sun, right? The Earth's in motion. So this was their presupposed stance on how to interpret everything, right? So when they did the Michelson-Morley experiment, they, according to the math and the framework and everything that they came up with for orbital mechanics and such, they were like, hey, we're going to go at 30 kilometers a second. and that's probably what we'll detect, right? Because we know we're in motion. Because if we're not, then like that means that we're been wrong for like 500 years, and that's not fucking right? So they do the experiment, they get the 8 kilometers, and they're like, "Fuck, what do we do?" So Lorentz comes along, and he's like, "Hey, maybe the ether is like hitting the matter and it's contracting, right?" So that's the hypothesis for Lorentz contraction, right? So then Einstein comes along, he's like, "Well, hold on a second. How about this, bros? The whole entire coordinate system contracts, and then it's just the speed of light that's the same." So they've done a complete divergence from experiments that prove anything or give relative results, because their framework of interpretation led them down a road of physically meaninglessness, and we're looking at the results of that now. Does that answer your question? Oh yeah, and the Sagnac effect and shit like that, like all that shit, proves an absolute reference frame. And then so they were like, well, it's not. So then they were like, well, it's not a the Sagnac apparatus isn't it's a non-inertial frame, so it doesn't apply. Well, then it was proven to apply, and still like that falsifies relativity on the face of it too. And they still go along with it and do make believe and pretend and stuff. It's physically meaningless.
Can you explain to me what a tensor is?
Yep. So a tensor is used to describe the geometry of spacetime, or what's going on within spacetime. I got definitions on it here that we go over. Analysis. Tensor, a mathematical object that represents a linear relationship between a set of vectors or scalars or other tensors. And this would be your tensor here. So this is whatever the fuck that's supposed to mean. And then these here are indices. Each indice of the tensor represents a 4x4 matrix, which represents basically any given, it can represent any given position in the infinite space-time coordinate system. And you use these to describe the distribution of mass and energy in the system, and you use these to describe like the conservation laws and things like that. So did you hear the cake contraction analogy?
I've been here from the beginning. Yeah, I listened to the whole thing.
Okay, yeah. So yeah, it's like to the cake contraction. So when you impose mathematical restrictions on these tensors, you can extrapolate information from it in regards to what's happening in the system. That's what the tensors are, how they function, what they do. And then this guy right here, actually, let me see if I can find the video. If you want to see a video of somebody contracting a tensor, so you can actually see what that process looks like, I have a video that you can use for reference. Stephen Crothers.
Was that the I-beam?
No, different beam. So this guy does a video presentation. Oh, wait, that's not it. That's a fucking screenshot of the link. Second. God damn it, did it again. Are you fucking kidding me? Because it is really interesting stuff. It's very high level and all that shit. It's crazy. But yeah, this dude, Stephen Crothers, who did his work on he went to the University of New South Wales. He was doing he was building a computer system for simulation of galaxies and all that kind of shit. He was super into the heliocentric lore, big fan of it. And then he was going to get his PhD candidature or whatever, and he decided that he was going to do his PhD in doing a mathematical analysis of relativity theory. And he does the tensor contraction on the pseudo tensor used to satisfy the conservation laws, and he finds out that it's a first order intrinsic invariant, whatever the fuck it is. I never remember the name. He realizes that it's not part of the system that it's supposed to be. It's not derived from the system, so it therefore breaks the mathematical validity of it. And he went through a ton of hell to try and maintain his candidature, publishing his work and stuff. And basically, what happened was they dropped his candidature. They without having someone to sponsor him, he couldn't get it, and his sponsor got bullied into dropping him. So he couldn't get his PhD in it, and he ends up arguing. He takes it all the way to like the International Gravitation and General Relativity Commission, and he's like emailing these dudes his work, and they're like talking to him, and every correspondence he has with them, they never address what he's saying directly or provide any anything into what he's saying, they always dance around it and then like start doing mathematical equations that aren't related to what he's even talking about. It's like it's very crazy where like they can't address it at all, and that has just really revealed itself to be like a big problem, like his discovery or whatever. Because when I continued researching into what he was talking about to try and figure out what this first order intrinsic shit is and what the implications are and what physically meaningless equations and shit means and all that, I came across the stuff from the Russian dudes that did the analysis, people that knew about this stuff beforehand, and like this is like an ongoing thing that they've just kind of largely ignored and pretend, and then they just hand down the equations to people that can solve them without doing tensor analysis and stuff, and then they do the equations and it works out, and they're like, oh my god, we just predicted the perihelion precession of the blah blah blah, you know. But yeah, that's a really cool video. That link there, you can actually see what it looks like when he does it.
Oh, did you put it in general or something?
Oh, I did. I'm sorry. I put it in the. I think did I put it in the wrong chat? Is it supposed to go not in general?
No, no.
Oh,
I
okay.
just not. I'm at work, so I gotta.
Oh, gotcha. Yeah, it's in general. It's in general. All right. So how we doing, guys? We all caught up? Any further questions? Anything like that?
I think it's great Professor Parks came in and you schooled him.
Dude, I love Professor Parks, man. I've known him for a long time.
Have
And,
you?
Yeah, dude. Bro,
How
look
does that
at.
work?
I met him through a YouTuber called I Can Science That, which who I also really like. He's a good guy, more honest about this stuff than most people, you know. It in return in terms of being on the opposite end of the flat Earth, being on the globe side, you know. So anyway, he's a super cool dude, and I talked with him one time when I was on with I Can Science That, and we just hit it off a little bit, and I hit him up every now and then, and we talk and stuff, and I just really respect him. And anytime I ever asked him a question or brought something to him, he always answers, and and he doesn't like bullshit me or try and dick me around. So yeah, like even on my YouTube videos, I promote him and I Can Science That on in my description, like for people that want to know more about heliocentric lore. Like I refer them to those two guys because I view them to be honest, good, genuine people that will talk about this stuff coherently and straightforwardly and not misrepresent it or try and obscure things. So yeah, I've known him for over a year.
Oh, nice. So when you came out with this presentation, he's been like ducking. He's been invited to it 3 times, I think. Right? We've talked about it with him. You try to get him to watch it, and he still hasn't watched the whole thing, huh?
Well, I mean, he's busy, you know. He is a professor or whatever. I'm sure he does stuff. And,
I mean, like he spends hours talking to us on Discord, so I don't know
Yeah.
how busy he is.
Oh yeah. True. Yeah, there is some element of that to it, I'm sure. But yeah, he's got his own shit going on. I mean, I don't expect
Sure.
anyone to review this shit and give me a fucking.
Well, I mean, like I would if before you throw shade and cast, criticisms and try
See,
to correct
see,
you.
that,
Probably would.
see, that was starting to irk me because, like I said, I really like that guy, really like him. But he's like starting to just like you didn't do. It's like, dude, I went over all of it. I just did.
You're just an acolyte of Witsit. Dismissed. Everything you said is dismissed.
Dude, that really irks me, man. Because if I don't talk like that, I literally lose momentum and I get fucked up, and then I got to get back on track. And it's I'm sure you guys noticed that during the presentation. Whenever I come out of a Q&A and start reading again, I'm all fucked up for a couple paragraphs. Like that's just if I start talking about it and I lose my train of thought, then that's a wrap, dog. That's a straight blackout. So there's gonna be a really long pause if I don't get it all out. And then when and like in terms of interrupting or over talking or whatever, only because I will lose what he's talking about, as he continues on. You know what I mean? Because there was some other stuff I wanted to talk about with that other guy in regards to space-time, because they're like, well, what about the space-time curvature? It's like, buddy, the whole presentation just proved there's no space-time curvature. Like, what do you mean?
Over. Didn't listen to anything you said. Started with your base argument. Gotcha.
dude, I was like kind of perplexed. And but it's all good. It's good to get out there and experience it, so I can have more experience in presenting it, because I think this information is solid as fuck, man. Like I said, I went through all this. It's all based off of peer reviewed stuff. It's not just like, not all of it's my opinion. Like this is stuff formulated from people that are in the mainstream academics and you know went through all that shit. And it's
Yeah,
just it's
I
basically
particularly
just
liked when someone asked you a stupid question, and then you said, "Shut up."
oh, did I really? I don't even remember. I don't even remember. I was on fire, dog. That was when I
You were
was
like,
like,
"Sit down and shut up, boy." Yeah, it was true because it was like an obnoxious, interruptive question too. It wasn't like a real
yeah,
substantive. I was listening and I want to know something question.
yeah. I don't even know what it was, but whatever it was, it just instantly registered as spam. So I just was like, shut up.
That was my favorite part. I think it was Alex BB who is that type of global.
Yeah. Yeah, but if you guys enjoyed it, please share it. I'll link the video later. You guys share that. Definitely download the PDF, share that, read it over, learn what's being talked about here. It'll help you understand the relativistic framework that's proposed that supposedly explains everything and all these things. Like I was saying, like I was going over the dark matter stuff when Parks popped in at the end, and I'm like, you know, is this accurate to how you say dark matter works? He's like, yep. So like I don't have a history uh of like you know
Mi-
of just like
making
making
shit
of
up.
just like
Yeah.
making shit up. You know what I mean? So like you know, let that serve as a little indicator that okay, maybe I should take it more seriously. And definitely check the sources. Don't just believe me because my interpretation aligns with what you think. Read the sources, see if you come up with the same conclusions. And if you need further help figuring stuff out, what I found to be a really helpful tool is you can copy paste sections of these papers and stuff directly into ChatGPT and ask it for an analysis of what's being said, ask it to extrapolate further on different terms, how they're applied, things like that. And once in doing that, you could formulate a better understanding of what's going on. It's super helpful in that regard. And
You can have ChatGPT make shit up for you.
yeah, exactly,
Oh, Demon Stride. What a
exactly.
glober. Dude, your
No,
globular is
hey,
spoken out.
No,
You might
and
want to
what's the
contain
thing?
that
no,
before it gets
And what's the
offensive.
thing?
he's just
What's the
he's
thing
just
where they
joshing.
use ChatGPT to explain a bunch of science shit, and it gave them a bunch of references and everything? The
Mhm.
references themselves were even made up.
Oh yeah, I'm familiar with that. I've asked it for source stuff, and it'll be like, oh yeah, dude, if you want to know all this red shit, check out this book. And then like the author doesn't exist, the title of the book's not real. So yeah, no, there definitely is stuff like that, and that's why you got to double check on it. But for the most part, when you ask it mainstream stuff, it does give reasonably accurate stuff, and then you can verify further from there, check definitions. It's a really efficient way to get to get a foothold into what's being conveyed, and then you can go from there further. And then in terms of
Information aggregate.
yeah,
Yeah.
in terms of understanding it, because a lot of the mathematical analyses, dude. So what's really cool about the math stuff is as I actually took the math stuff from Crothers's papers, and I put it in Chat GBT, and I'm like following the logic of the math, and how it's being applied. Does it support this conclusion? And like I'll put like XYZ conclusion about whatever Crothers said or whoever said anything about whatever math they're using, and it'll be like based on the blah blah blah, it's it's all on the up and up and looks correct and stuff. So even though that does get stuff wrong too, I'm not going to say that it doesn't. It's still helpful in that regard because when you put stuff in that's garbage, it'll be like, nah, that doesn't work at all. So it does give interesting results where you can kind of narrow down how true or how likely something is to be accurate, based on that. Because every time I ask a high level math guy I'm like, hey man, this Stephen Crothers guy is contracting tensors, talking about first order intrinsic invariant differentials. What's going on? They're like, oh, I don't know how to contract a tensor. I can't do that. I mean, it's way above my head. All I can do is calculate the perihelion precession of Mercury. So it's like, all right, man. So like it's a subject that nobody wants to really touch on, man. The math analyzation stuff because it's such a high level subject, and then going through these papers, if you just try and read this without like these definitions laid out to give you a baseline and stuff, none of it's going to make any fucking sense. Like I've known about Crothers for a long time and the first order differential thing for a hot minute. Had no idea how to figure out what it is because no one even fucking knows, really. Like it's hard information to find out. But once you understand like what he's talking about, how it's a tensor, how it's related to the transformations and all that, you're like, oh, okay, so it's all this shit, and this is supposed to represent a matrix within the system, and then you impose restrictions on it, and that's why you find out what's happening in this. Oh, you know what I'm saying? It starts to coherently make sense in an intuitive way after you have hundreds of hours of conversations about it with a bot that so And living people, obviously. But yeah. All right. So if there's no further questions or anything like that, I'm gonna head off, man. I'm beat.
That was great. I'm glad that you recorded it because I don't think I'm glad that you recorded it in an audio top notch version.
Yeah, thanks, man. It's I'm gonna upload it now.